Hello my dear NEET aspirants and welcome you all to your own platform PW. This is your physics mentor Gaurav Tiwari and today my dear kids will learn the concepts of laws of motion. My dear kids, this is a very interesting chapter and it is filled with lots of interesting demonstration that I'll be showing you over here. You'll be learning the concepts of Newton's laws of motion, lots of concepts of pulleys, constraint motion, concepts of conservation of momentum and a lot of other things, right? So just stay tuned. By the end of the class, you will find that every concept is crystal clear in your brain, and not just that, by the end of the class, like always, I'll be sharing the lecture notes and the DVP through the link given in the description. My dear kids, PW is constantly changing the ways we learn in the most affordable ways. You can also figure out a lot of interesting ways this can facilitate your learning through the link given in the description. Now, let us start this chapter right away and start learning this chapter. So, alright my dear NEET aspirants, if you just go ahead and look at the syllabus of this chapter, in the NEET syllabus, you'll find all these topics are mentioned into it. And if I try to write it down in a list format, these are all the topics. So, there are a lot of topics that we need to cover, right? But if I try to segregate it so that we can make a strategy around it and we will develop our understanding around that strategy. So, have a look at that. So, for the better understanding, we have divided all the topics that were mentioned in the NEET syllabus in 4 parts, right? So, understand that how are we going to cover it. In the first part, I'll be dealing with the terms force, impulse, momentum, relation between impulse and momentum, right? And then law of conservation of momentum. These things we'll be talking about in the first section, very important section. You will find that many times direct questions are asked from this particular part in the NEET exam. A lot of numerical solving we'll be doing as well in this first part, right? Now, the second part of the strategy is we will be talking about the FBD and constraint motion, right? Now, the constraint motion is super important for JEE, but when it comes to NEET exam, simpler problems are asked from the constraint motion, but however, I will be explaining you much difficult problems from the constraint motion as well, so that there is nothing that haunts you anymore in this segment as well. So, we'll be giving enough time to the second part as well, right? In the third part, there is friction. So, needless to say, we'll be talking about friction and types of friction. So, in this one, apart from rolling friction, be it static or kinetic, both the frictions are important for you. Yeah, you have to talk about that. Rolling friction, the problems on rolling frictions are not asked in the NEET exam, but I'll be giving you a brief about the rolling friction as well, right? But mostly we'll be solving the problems on the static and kinetic friction, right? And then in the last part, we have the dynamics of circular motion, right? So this part we will be not covering in this one shot. Here I have done one thing. I have created a separate one shot for circular motion only. So the kinematics of circular motion, where you will be discussing about the velocity and everything else about the circular motion, and the dynamics of circular motion. What are the forces involved in the circular motion? For example, if I take this body and start rotating in a circular path like this, right? So this rope is under tension, right? So at different points of the circular path, what is the tension in the rope? All those calculation of forces, when we are going to do that, we will talk about the dynamics. Dynamic analysis means analyzing the forces acting in the system. So we will be doing the dynamics of circular motion along with the kinematics of the circular motion in a separate one shot, and we will call that separate one shot as circular motion itself, right? Okay, so everything of circular motion will be discussed in that. So we'll be not talking about the part 4 here. So part 1, 2 and 3 will be discussed in this chapter, and every topic that comes under the sun in these 3 topics, as for the NEET syllabus goes, we'll be talking about those things in a very precise manner, right? So that is our strategy. Now let us move ahead and talk about the first part, and that is going to be a very detailed part, right? So let's have a look at that. So it starts with a word called inertia. What do you mean? What do you mean by inertia? Now the inertia is a tendency of a body to resist any change in the state of motion, right? What does that mean? You see that I talked about a term called a state of motion, right? So when I say that a state of motion of a body, I mean 2 things, my dear students. When I talk about a state of motion, I mean 2 things. What are those 2 things? How fast the body is moving, that is the speed of the body, how fast the body is moving, and in which direction the body is moving, right? Both the terms together form the word state of motion, right? You see that if a body is moving like this with 20 meter per second, right? I'll say that it is moving with 20 meter per second in this direction. Let's say this is east. So it is moving with 20 meter per second towards east, right? Now, it will not change its direction on its own. It will not automatically, without any influence, external influence, it will not change the direction, right? You need some force, you need some influence on the body, you need some effort so that you can change any of these two things, right? Okay. Now think about it. There are two bodies. One that is a small body that is moving on the ground, right? And let's say that you want to either stop it, or you want to make it move faster, or you want to change its direction. Compared to the case when you have to do the same thing with a larger body, right? Let's say that this is a 1 kilogram body and this is a 100 kilogram body, right? 100 kilogram ball is rolling towards you and you want to stop it, and a 1 kilogram ball is moving towards you and you want to stop it, in which case you have to apply larger force. So we can say that, of course, in the 100 kilogram case, right? And of course, we don't want to stop it. We want to, move aside out of this path. So the thing is, the tendency to maintain its motion is higher in this one than this one, right? So we will say that the inertia of the second body is higher in the second one as compared to the first one, right? So in general, whenever we talk about inertia, we look at the mass of the body, right? So mass is a very good measure of inertia. Heavier body generally have higher inertia, or we can say that they have a higher tendency to resist any change in their state of motion, right? So if they are moving, they want to continue to move, right? And if they are stationary, they want to remain stationary. And if you want to do any change with them, you need higher values of forces, right? So more inertia means you need more effort to change their state of motion. I believe the idea is very, very clear, right? So now let's talk about it. What is force? So we know that some basics, right? So force is nothing but a push or a pull applied on a body. And why do we apply force? To deal with the inertia of the body, right? We apply force to deal with the inertia of the body. So you see that this block was maybe stationary, and when you start applying force on it, it will tend to move, or it will move actually, right? So this is the force. Force is something which changes the state of rest or motion, or we can say the state of rest or motion of the body. So it causes the body to start moving if it is at rest, or it stops it, right? So yeah, it is measured in newtons, right? It's a basic stuff, you might know it. Now what are the types of forces? Contact forces and non-contact forces, right? So in certain situations, when you have to apply force, you have to make a physical contact with the body. For example, if I want to move this remote, right, I cannot move this remote without actually touching it, right? But let's say that there are two magnets and they can apply force on each other without actually touching each other. So that's a non-contact force. So yeah, so contact forces and non-contact forces is about if the bodies applying force on each other are actually touching or not. Gravitational force, you can say that even if the body is in the air and this is earth, body is still attracted toward the earth, it can be called as a non-contact force, right? Now look at the contact forces. Friction force can only come into the picture when two bodies are rubbing against each other. Normal force, the normal force is basically when a body is placed on a surface, so a normal reaction is offered to the body, right? So that is a normal force. So spring force, that is also a contact force, we can say. So non-contact forces, this is a non-contact force between magnets and between earth and a body, the gravitational force, and the electrostatic forces are also non-contact by nature. Now, if I talk about Newton's laws, right? So Newton's laws, you already have some basic idea about the Newton's laws, and we're solving some problems on it as well. Now let me tell you, there are most number of problems on the second law, Newton's second law, right? We'll be solving in a short while. Just let me explain you the basic terms first, right? So don't rush, right? If you know something, just revise it. And if you don't know something, just learn it, right? So here it is, Newton's first law of motion. So what is Newton's first law of motion? It talks about inertia, right? It talks about inertia. It says that every body has a tendency to resist any change in its state of motion. And if you want to overcome that resistance, then you have to apply a force, right? So without an application of force, you cannot change the state of motion of the body. That is the first law. That means a body, if it is stationary, it will remain stationary. And if it is moving at a certain velocity, in a certain direction, it will maintain its velocity in the same direction unless you start applying a force on it. So a force is needed to deal with inertia. That's the first law, right? So momentum, what is momentum? Now in physics, whenever we try to deal with the effect of forces, right? So the best term that can help us to understand the effect of forces when we are talking about the dynamics, right? This chapter of Newton's laws of motion, we can rename this chapter as dynamics of the bodies, right? Dynamics of the moving bodies. So basically, whenever we talk about the dynamics of bodies, we are dealing with the forces involved into the picture, right? Whether they are stationary or they are moving, right? So right now, the best tool to understand the effect of forces on the system is momentum, right? Momentum is just a term that we have made up. It's a product of mass of the body and how fast that body is moving, that the velocity of the body. So velocity being a vector, the product of mass and velocity also becomes a vector. So momentum vector is mass times velocity, right, of the body, right? So here it is, momentum is a vector quantity, right? It's a product of mass and velocity. Let's move ahead and talk about the next part. Newton's second law of motion, what is that? First law talks about inertia. Second law talks about the value, the second law talks about the momentum, right? Or you can say in this way, how much force you need for a particular change that you want. Let's say that first law, I already told you that if the body is moving, let's say at 20 meter per second and you want it to change, right? Let's say you want to make from 20 to 30, 20 to 40, you need a force, right? Because the body has inertia. It has a tendency to resist any change in the state of motion. And second law is talking about how much force do you need for a certain change, right? So if you want to make it from 20 to 30, initially it was moving at 20 meter per second and then you want it to move at 30 meter per second in the same direction. Then how much force you need? In the comparison, if it was moving at 20 and now you want it to move at 40, of course you want it to move it much faster, so you need higher value of force. How will you calculate that force? How will you calculate the amount of force you need for a certain change in the state of motion? That is something you can understand with the second law, right? So second law talks about the amount of force for a certain change in the state of motion, or we can say the momentum of the body, right? So we can say that second law talks about that the value of force you need is proportional to the rate of change of momentum, how quickly you want to change the momentum of the body, right? The value of force you need is proportional to the rate of change of momentum of the body. If you want to change the momentum of the body much quicker, you will be needing a higher value of force. Think about it. This is the body, right? In the case number 1, and in the case number 2 again, you have the same body. Don't have a different body. Again, same body you have, right? In the first case, I'm saying that you have 10 seconds to move this body from this body, let's say was initially moving at 10 meter per second, right? And in the first case, you have 20 seconds in your hand, right? To increase the velocity of the body from 10 meter per second to, let's say, 20 meter per second, right? So I'm giving you 20 seconds to increase the velocity from 10 to 20, right? But in the second case, I want the same thing. I want you to change the velocity from 10 to 20 again in the second case, right? I want you to change the velocity of the body from 10 to 20 again, but this time I'm not giving you 20 seconds as I was giving you in the previous case. This time I'm only giving you 5 seconds. Clear? So in the first case, I gave you more time to create the same change. In the second case, I gave you lesser time to create the same change. So in which case, of course, in both cases, you want a change in the state of motion. So you need force, in which case you'll be needing more force, right? So we can say that in the second case, we'll be needing a higher value of force because we want the same change of momentum. You see that here, if the body had a mass of, let's say, 1 kilogram, so 1 into 10, initial momentum was 10 units. Final momentum was 1 into 20, 20 units. Change in momentum is 20 minus 10, 10 units. In the first case, you are changing the momentum by 10 units. In the second case, you are also changing the momentum by 10 units, right? So the value of change in momentum that you want is same. But in the second case, you have more time. In the first case, you have more time. In the second case, you have lesser time. So you want that change of momentum to happen much quicker. So that is why you need a higher value of force, right? So force is proportional to how quickly you want to change the momentum. Force is proportional to how quickly you want to change the momentum. So force is proportional to rate of change of momentum of the body. Whenever you remove the proportionality sign, a constant is introduced, and let us call that constant is k. So F is k times dp by dt. I believe the idea is very, very clear. Now, this is how you will learn the second law. You will not call it F is ma. That is there. But this is much better form, and you can understand the law of conservation of momentum much better if you go with this form initially, right? So this is the second law, Newton's second law, right? So I believe the idea is very, very clear. So k is constant, right? So what is p? P is momentum. So if you want, you can put the value of p is mass into velocity over here. In place of p, you can put mass into velocity. Mass of the body is generally constant, right? When a body is moving, its mass stays constant. In some cases, it is not, like a rocket. A rocket has huge amount of fuel in it, and as the fuel is burning and gases are coming out, the rocket is losing the fuel, right? So as the rocket is rising up, it is getting lighter and lighter, right? So during the motion of the rocket, its mass does not remain same. But in most other cases, when a vehicle is moving, or when a body is moving, we can say that its mass remains constant. And if mass is constant, it can come out of the differentiation sign. And when it comes out of the differentiation sign, dv by dt remains inside. Rate of change of velocity, dv by dt, is acceleration. So instead of dv by dt, you can put ma, right? So k, the value of constant, comes out to be 1 with experiments, right? So force becomes 1 into m into a, or simply m into a. This was the format you learned in grade 9th, right? Force is mass into acceleration. So I believe the idea is very, very clear. This is the format we already know, but this is the format we need to be habitual with. So force is dp by dt. The value of force acting on the body is equals to rate of change of momentum of the body. You will talk about this format now onwards, right? So according to second law, Newton's second law, what is the value of external force acting on the body? It is dp by dt. I believe the idea is very, very clear. Now let's move ahead and talk about the next idea, right? Yeah, so now let's talk about the next idea. So here it is, here you have a word called equilibrium. So you see that, let me just explain you that. There are various aspects to this word, but for now what is written, let me explain you. If a body is not accelerating, let's say a body is moving in this way, right? It is moving with 20 meter per second, right? Let's say that when the body was moving, two people were there. Let's call the one person is Ayush, right? And second person is Piyush. Ayush and Piyush, right? So you see that Ayush and Piyush both are applying the forces on the body. So if one person is applying the force on the body this way, the other person is applying the force on the body in this way, right? While the body is moving in this direction with 20 meter per second, Ayush is applying the force of Ayush is in this direction, force of Piyush is in this direction. But still we found that the velocity is not changing. It was initially moving with 20. Even after the forces are applied, the body is still moving at 20. So what do we understand by this equation? What do we understand from this situation? We can say force applied by them must be cancelling out because we see that even if they apply the force, the velocity is not changing, or the acceleration of the body is 0, right? Yes or no? So we can say that the acceleration will be 0 only when the net external force is 0. The net external force is 0. All right. The acceleration will be 0 only when the net external force is 0. So anyone can make a simple question out of this, that if a body is moving with 20 meter per second or 30 meter per second, let's say, right, and there are 4 people are applying forces on it, right? Let's call them person 1, 2, 3, 4, right? 4 people are applying forces on it. So force number 1, 2, 3 and 4, right? 1, 2, 3 and 4. If the force applied by 1 is 20 Newton, Force applied by 2 is 30 Newton. Force applied by 3 is, let's say, 40 Newton, and you don't know the value of force applied by 4, right? The forces are applied parallel to each other like this, right? So you have to calculate it. It is given that even after the forces are applied, the velocity of the body does not change, right? So how will you calculate the value of force? We can say that from the second law, if there is no change in the velocity, that means there is no acceleration. It means there is no net force acting on the body, right? And if there is no net force acting on the body, forces acting towards right must be equal to forces acting towards left, right? So F1 plus F2 must be same as F3 plus F4. So F1 plus F2, which is 50, must be same as F3 plus F4. Let's call F4 is X. So 40 plus X. So X will become 10 Newton. So I believe the idea is very, very clear, right? The fourth missing force is 10 Newton. So that's a very simple thing. Now you see that this is another thing, right? So let's talk about more important points. Second law is strictly applicable to a single point particle. We will talk more about that. Right, so here you have look into this question. Let's try to solve this question. The force acting on the body is this, and the acceleration it accelerates the body with 1 meter per second square. What is the mass of the body? So mass of the body is of course a constant. The force is given in a vector format. So let us try to first get the vector format out of the equation. So what will be the magnitude of this force? So the magnitude of this force I can write in this way. I can also write in this way, right? So under root this square, this square, this square. So it is under root 6 square, 8 square, and 10 square. So 6 square is 36, 8 square is 64, which is 100. 100 and 100 is 200. Under root 200 is 10 root 2. All right. So it accelerates with 1 meter per second square. The value of acceleration is given as 1 meter per second square, right? So now what is happening? You have to calculate the, mass of the body. So force is mass times acceleration. So what will be the value of mass? It is force 10 root 2 upon acceleration, which is 1. So again, it is 10 root 2 kilograms. So we can say that option B is correct option here, right? So I believe the idea is very, very clear, right? And there is no confusion with this particular part, right? So here it is. Yeah, 10 root 2 kilograms. Let's move ahead and talk about the next question right now. So the next question is saying that a ship of mass that many kilogram initially at rest, right? Initially it was at rest. Initial velocity of the ship was 0. This is the mass of the ship, okay? So mass of the ship is given, okay? It is pulled by a force of that many Newton. So this is the value of net external force acting on the body. It is pulled by the distance of 3 meters. So you are pulling a ship on the water through a distance of 3 meters, okay? You are applying a force for it. So that is a distance traveled by that ship, right? You can call it D or S, right? Assuming that the resistance due to the water is negligible. So when the ship is moving on the water, the resistance between the ship and water is negligible, right? What will be the speed of the ship? So what will be the speed of the ship? Initially the ship was at rest. It is written initially the ship was at rest. But since you are applying an external force, its state of motion should change, right? So since you are continuously applying the force, its state of motion is changing, its velocity is increasing. You still apply the force, velocity will continuously change. You still apply the force, velocity will continuously change. After the ship has traveled for 3 meters, what is the new velocity it has acquired right now? So you can say that since you are applying a constant force, right? 5 10 to the power 4, a constant force will bring you a constant acceleration, right? A constant force is equals to mass times acceleration, no? Right? So if force is constant, acceleration will be constant, or if force is variable, acceleration will be variable, and vice versa, right? Remember that. So here it is, you can say that the velocity it will acquire, v is equals to v square is u square plus 2as, right? Because we have to calculate the velocity after a certain displacement, right? It has traveled 3 meters. What will be the new velocity? That is why we are applying this equation, right? These 3 equations of motion are applicable when the acceleration is constant, right? Acceleration is constant means the force is constant, right? So whenever you see the constant forces acting into the picture, all 3 equations of motion that we had learned will be applicable, right? So here it is. Initial velocity was 0. So final velocity is 2 times acceleration to displacement. Do we know the value of acceleration right now? We know the value of mass and force. So clearly we can calculate the acceleration, which is force over mass. All right, into displacement. So what is the value of force over here? 5 into 10 to the power 4, and mass is this 5 into 10 to the power 4, and mass is how much? 3 into 10 to the power 7. Right, so here you have displacement. Displacement is 3 meters. So right now you can just cancel things out and you can just solve it. So you have 10 into 10 to the power 4 divided by 10 to the power 7. That will be the square of velocity. That will be the square of velocity. And when you solve it, you have 10 to the power 5 upon 10 to the power 7. So basically you have 1 upon 10 to the power 2. So when you take the under root, velocity is 1 upon under root of this thing is only 10. So it is 0.1 meter per second. This is the new velocity it will achieve, which is the option number A, right? So option A is going to be the correct option. I believe the idea is very, very clear, right? So here you see option A is correct. Now let us move ahead and talk about the next question. So the next question is saying that a boy is pushing a box of mass 2 kilogram with a force of 20I plus 10J, right? 20I plus 10J, okay. Is it a constant force? Yes, it's a constant force. It will bring upon a constant acceleration. And if we need, we can apply the 3 equations of motion. V is u plus at, S is ut plus half at square. Those equations of motion can be applied to analyze the motion created by this force. If this force was a variable force, then the acceleration would also be a variable acceleration that will change over time. So in that particular case, those 3 equations of motion we won't be able to apply, and we won't be able to analyze the motion caused by that variable force in that situation, right? So mind that here you have a constant force, so we are free to apply those 3 equations of motion, right? Okay, so you have a mass of body 2 kilogram, you have this force acting on the body, okay, and it is moving on a frictionless surface. If the box was initially at rest, so initial velocity of the body was 0, then dash is the displacement along the x-axis after 10 seconds, right? So you have to talk about the displacement after some time caused by a constant force. Constant force will create a constant acceleration, and we can apply the equation of constant accelerations, right? So which is equation of uniformly accelerated body. So we have to talk about the displacement after some time. So S is ut plus half at square. S is ut plus half at square, right? So initial velocity was 0. So this term will not be there. So you only have half at square. Acceleration you can get from by dividing force and mass, right? So here you have the displacement. So everything you can put in a vector format. You can get the final displacement also in the vector format. No need to worry. You have to talk about the displacement along x-axis, not the net displacement. Mind you, we do not have to talk about the net displacement. We are talking about the displacement along x-axis. So acceleration here is force by mass. Force is 20I plus 10J. Write it. 20I plus 10J divided by force by mass. Mass is 2 kilograms, all right, and is into multiplied by time. So time is 10 seconds. So square of 10, all right. So you just multiply that, all right. So here you have it. So 25 into 20, which is 500, and 250. Okay, I believe the idea is very, very clear, right? So you have this displacement vector coming for yourself right now. So you have to talk about how much displacement it will cover along x-axis. So you see that coefficient of I is the displacement along x-axis. Coefficient of j is the displacement due to this force along y-axis at the end of 10 seconds, right? So we have to talk about at the end of 10 seconds, what is the coefficient along x-axis? So this is the answer, right? What is the displacement along x-axis? So displacement along x-axis is 500 meters. I believe the idea is very, very clear, right? So you see that is the answer. Let's move on and talk about the next question. So the question is saying right now, my dear kids, that a body of mass 2 kilogram is moving under a force of 2i plus 3j plus 5k. You see that it does not depend on time or it does not depend over displacement. So it's a constant force. And it starts from rest and was at the origin initially. All right. So it was at 0, 0, 0 origin and it starts from rest. Okay. Initial velocity of the body was 0. Right. Mass of the body is given 2 kilogram. And this is the force acting on the body. All right. So after 4 seconds, its new coordinates are 8b20. Okay. So after 4 seconds, so that is the time, its new coordinates are this. What is the value of b? So basically we have to talk about the displacement vector at the end of 4 seconds. So after some time, what will be the new displacement? So coefficient of I is this, at displacement along x-axis, coefficient of j is displacement along y-axis, and coefficient of k is displacement along z-axis, right? So whatever the displacement vector comes out, that will give us the idea of x, y, and z, right? Okay, so let's have a look at that. So here we have to talk about the displacement caused by a constant. Here we have a constant force, so uniformly accelerated motion is going on. Right, so displacement is s is ut plus half at square. Ut part will become 0. Only half at square will be there because the initial velocity of the particle was 0. So I'm only writing this much. So what will be the final displacement? Here you have half. The force is 2i 3j 5k. 2i plus 3j plus 5k. Okay, right. This is the value of force, and you have to divide the force by mass, which is 2. And the time for which the body moves is 4, a square of 4, because t square is there, right? So 4 into 4. So this 4 and these two things will be cancelled out, right? So what will be the displacement vector? So just multiply the 4 inside. So it is 8i cap plus 12 j cap plus 20 k cap. This is the displacement vector due to this force into this picture. The coefficient of I is the displacement along x-axis. So this is Sx, this is displacement along y-axis, and this is the displacement along z-axis. So here you have 8, here b you have 12, and here this part is 20, right? So basically the idea, we have to answer the b part, which is 12. So correct answer is b is 12 over here. All right. So that's it. Let's move ahead and talk about the next part. All right, so let's look into this question and try to solve it as well. So here you have the question. A body of mass 4 kilogram is experiencing two forces. First force is this, second force is this, right? You see that the first force does not depend on time anywhere, right? It is written 5t, 8t square like that. So it's a constant force. And second force is also a constant force. The acceleration acting on the body is. So here we don't have to talk about the equations of motion. Here we have to talk about acceleration. Now think about it. What decides the acceleration of the body? Right. When I was discussing the second law and I was explaining the multiple forces acting on the body and the body was not accelerating, when I was giving you that example, I told you the net force acting on the body decides the acceleration of the body, right? And here we have to calculate the acceleration. So as I said, acceleration will be decided by the net force acting on the body. Even if the individual forces are not 0, if you add them and the net force comes out to be 0, then the acceleration caused by the combined effect will be 0, right? So here F1 is 5i, 8j and 7k, right? And here F2 is 3i, 4j and 3k. So if I combine them, right, so what will happen? Net force will be F1 plus F2. So 5 and 3, 8. 8 minus 4 is 4j and 4 minus 3 is 4k. This is the net force acting on the body, F net. And this force will be deciding the acceleration of the body. So what will be the acceleration? Mass of the body is 4 kilogram. So acceleration will be net force divided by mass of the body. So which is this 8i, 4j and 4k divided by mass, which is 4. So if you divide this thing by 4, it will be 8 by 4, which is 2i, 4 by 4, which is only 1j, and 4 by 4, it is only k. So I believe the idea is very, very clear. 2i plus j plus k, which is the first option, 2i plus j plus k, that is correct over here, right? So I believe there is no confusion over here. Let's move ahead and talk about the next numerical and have a more clear understanding about the laws of motion, right? So here it is. So at any instant, the velocity of the particle of a mass of 500 gram is this. So mass of a particle is given 500 grams. Everything else is given in Newton meter second. So we have to put the mass also in MKS. So SI system. So 500 gram is half kilogram. Okay. So we have the velocity of the particle is this. Now it's a slightly good question. You see, velocity of the particle is written as 2t I cap plus 3t square j cap. All right. So this is the velocity of the particle 2t I cap plus 3t square j cap. Okay. Now, if you look at this velocity, it's not constant. Velocity is changing with time, right? So you see, velocity is a function of time. All right. Now, you know that from the kinematics chapter, if you differentiate velocity dv by dt, you get acceleration, right? So differentiate it. Differentiation of velocity dv by dt will give you acceleration. It's a simple thing. 2t, differentiation of 2t is only 2. A differentiation of 3t square is 3 into 2t, which is 6t. I believe there is no confusion. Now when you look at acceleration, it is 2i plus 6t j cap. It is not 6 j cap, it is 6t j cap. That means for different values of time, when you put different values of time, acceleration at t equals to 1, 2i plus 6j. Acceleration at t equals to 2, 2i plus 6 into 2, yani 12j. Acceleration at t equals to 3, 2i plus 18j. So at different times, the value of acceleration is changing. So here you have variable acceleration, and when you have variable acceleration, that means the value of force that is causing this acceleration is also dependent on time. That is also a variable force. So if you had to analyze the motion in this case, you cannot use those three equations of motion, right? So here we have a variable force, and we have to talk about what is the force acting on the particle is this at t equals to 1 second, then what is the value of x, right? So you see that the force is variable, it will change with time, but we are talking about at t equals to 1, right? At t equals to 1 second, the value of force is this. Of course, the next second, the acceleration is changing. That means the force that has caused that new acceleration is changed, right? Okay. So acceleration is at t equals to 1. Put t equals to 1 over here. It is 2i plus 6 into 1, which is 6j. And the force that will cause this acceleration will be at t equals to 1. Force is mass times acceleration. Mass is half kilogram, right? And acceleration is 2i plus 6j at t equals to 1. So just multiply half, it is I plus 3j. And when you compare it, this force at t equals to 1 with the expression over here, you will find it, the coefficient of I is 1 over here, but coefficient of j is x here and 3 here. So the value of x is nothing but 3. I hope there is no confusion over here, right? And this is a slightly good question, just to check whether or not you can deal with the variable forces as well. And there was nothing very difficult in it as well, but I hope you have understood and you have a crystal clear understanding of these cases as well. Let's have understanding of further cases. Right. So here we have a new term called impulse. So we have talked about force, we have talked about momentum. Now we are going to look at impulse, right? It's going to be a very, interesting new word for us, right? So let's have a look at that word impulse. So impulse is when we talk about the effect of force that is acting on a body for a very short interval of time, right? You see that there are various cases when you don't only push or pull the body, right? You do that, you apply that push or pull, but you don't apply it for extended period of time. You apply it for a fraction of time. For example, when you are playing the bat ball or cricket, so you are hitting the ball with your bat, so you don't just take the bat along with the ball and slowly take it to the boundary along with the bat itself. You just hit it. So for that very small value of time, for a half second or 1/4 of a second, the ball is in contact with your bat, right? In that little time, you apply the force, and that force does the things. It changes the momentum of the body, right? So in those cases, we are actually dealing with impulse, right? We are dealing with impulse. Now, let's say that here we have a bat. Let's say this is the bat, right? And we have a ball over here. This is the ball, right? Let's say that we are trying to hit the ball over here, right? So just look at everything in slow motion. So this is how the ball is coming, right? And now it hits your bat, right? Now you hit it. Okay. Now for a very short time interval, let's say for half a second, it is in contact. The actual duration is even lesser than that. But let's talk about half a second. So what is happening? The ball is coming in contact, then it is coming in contact, and then it will rebound, right? So what will happen? The force will gradually increase, and then it will leave the ball. The force will gradually decrease, and then become zero, right? So the value of force during the impulse is not same, right? You see that when the ball is coming in contact, it is right now, just before the contact, there is no force. Now the value of force that is acting on it is increasing, and then it leaves the contact. So during the time of leaving, the value of force is reducing, and when the ball leaves, the force becomes zero, right? So the value of force, you see that whenever we are dealing with impulse, we are not dealing with a constant force. That's what you have to understand, right? You see, in this situation, let us say the force was acting for a very short interval for half a second. Let's say we have the value of time over here, we have the value of force over here, right? We have the value of force over here, F, right? You see that the force was initially zero before the body actually made the contact with that bat, right? So the value of force was zero. So initially the force increased, right? It peaked out, right? It peaked out, and then ball has to leave the bat as well. So the force will reduce and eventually become zero. So you see that the value of force during that little fraction of time was not constant, right? So in the case of impulse, we are not dealing with a constant force. Whenever we are talking about this F is the average force. So in this little time fraction, let's call it, this is half a second. Here it was 1 second, t equals to 1 second, and it is t equals to 1.5 second. At t equals to 1, ball comes in contact with the bat, and after half a second, the ball leaves the bat. So in this half a second, the force was changing, right? So we are dealing with this force over here is the average force. And when we try to talk about the impulse is average force into that time duration. Impulse acting on the body is average force into the time duration for which that impulse acts, right? So I hope the idea is very, very clear. And if this time interval becomes very fractional, right, like you call it, it is tending towards zero, you can also represent in the integral format. So integral, if it is acting for a time dt, then the impulse is ti to tf f dt, right? So if you want, you can read it now. It will make more sense. So impulse of a force is, which is the product of average force. Impulse is a product of average force during the impact and the time for which the impact lasts, right? So the average force and the time for which the impact lasts, it is measured by, so what is the value of, you can say, impulse? How much impulse has been imparted to the body? Now you see that there's a very popular shot played by our ex-captain Mahendra Singh Dhoni. So we used to call it helicopter shot. It used to carry so much power in it that whenever the ball used to touch the bat, it used to generally cross the boundary, right? So why is that? Because he is applying so much force in it. The average force during that fraction of time was huge, right? The average force was huge, which is, how do you get that? How do you get that if the force, if the impulse is higher or not? What is a visible outcome of higher impulse? So we can say that the ball reaching the boundary, right? That is the visible outcome of higher impulse, right? So you see that if this is the ball and I'm going to hit the ball with a bat, in two cases. Like Rahul Dravid, I just flicked it. So in that case also, the ball is touching the bat is touching the ball very slowly, but not with the intention of throwing the ball outside the boundary, right? So in the second case, you are applying less average force, right? In the second case, you are playing the helicopter shot. So your intention is to send the ball flying over the boundary, right? So in the second case, the bat is still touching the ball, imparting the impulse, but you have large average force, right? Large average force. So what will be the visible outcome of these two cases? When you have less average force, initially the momentum of ball was something. When you applied the less impulse, when you applied less average force, the momentum of the ball does not change significantly, right? But in the second case, the momentum of the ball changed significantly, right? So it is the momentum, by observing the momentum of the ball, by observing the change of momentum of the ball, we can say that we have imparted a greater impulse to the body, right? Yes or no? Right. So here it is. Here it is. So when you try to write it out, yeah. So this is the expression. Force is dp by dt, right? This entire observation is hidden inside this expression itself, right? You can impart greater value of impulse to the system, and that will be visibly, you can see it visibly by the amount of change in momentum it can bring upon. Yeah, this is visibly written inside the equation. Just look into the equation. F is dp by dt, right? So change of momentum is f dt. Change of momentum is f dt. What is f dt? This is impulse, right? And what is dp? It is change in momentum. Change in momentum, right? This is second law, na? Force is rate of change of momentum. So if you just rearrange the terms, it is also can be written in this way, that the change of momentum equals to the impulse imparted to the body. Very simple, right? So this is it. If you want to write the whole thing in an integral fashion, for a certain time interval ti to tf, f dt is the change of momentum in the same time interval, right? The change of momentum of the same time interval, right? So it is final momentum minus initial momentum, whatever that value is, that is equals to the integral of f dt, which is nothing but the impulse imparted to the body, right? So this equation relates impulse with the momentum. That is why it is also called as impulse momentum equation of the body. You can call it this way, right? Impulse momentum equation of the body, that the impulse imparted to the body is equal to the change of momentum of the body. Impulse imparted to the body is equal to the change of momentum of the body. And impulse momentum equation is just rearrangement of the second law. So anyone who has understood the second law, and anyone who is talking about the second law in this format, right, not talking about f equals to ma, right? If somebody is saying that f is equals to ma is second law and my life is going well with that, they will be feeling problem with that, right? Right now we have understood f is dp by dt. Force, external force is rate of change of momentum of the body. We understood this is the second law, and just by rearranging the terms, we found the impulse momentum equation. Impulse is related to the change of momentum of the body. Nice. Now, if you look at the graph, now the graph problems are also there. So if you look at the graph of this thing as well, so again a very simple thing, right? This is ft curve, force versus time curve, like this. So for a certain time period, if you take the area under the curve, integral t1 to t2 f dt, this term is representing the area under ft curve from this to this time, right? From this ti to tf, this area is representing the impulse imparted in that duration, right? So if I show you, this is the diagram of force versus time. So in this duration from here to here, if I take the area under the curve, that means for this duration, how much impulse was imparted to the body, I can calculate that. Look into this question and try to have a understanding of impulse in a much better way, right? So here you see that figure shows an estimated force time graph like this. So you see that the body is coming in the contact with other body. So right now you get the value of force is increasing and it peaks out, and now the ball is leaving the bat. So the value of force is reducing and becoming 0 again. So you see that the force is not constant, and here you have this variation shown in this picture, right? For a baseball is struck by a bat, so baseball bat and ball is there. So this thing is same. From this curve, determine the average force exerted on the ball. You know that when we talk about the impulse F dt, F delta t, so that F there is the average force, right? So here, you know that the area under the curve in this duration is representing the impulse. So impulse here is area under the curve. It is a triangle, and we know that the area of this triangle is 1 upon 2 base into height. So this is 1, this is 2.5. The base is going to be 2.5 minus 1, right? Only this much. So base is 1.5. And height is how much? 18,000. All right. So this is the impulse imparted to the body. And you know that you have to talk about the average force acting on the body. And you know, impulse is nothing but average force acting on the body for a time interval delta t, right? So you know the time interval is 1 to 2.5, that is total 1.5 seconds, right? So if you divide impulse with that delta t, I upon delta t, that will give you the average force in that particular part, right? So if you divide I by delta t, that will give you the value of force, right? The value of force over here, right? So right now, what is the value of delta t? It is 1.5 seconds. So just put delta in place of delta t, put 1.5 seconds, and you have your answer over there. 1.5 over there. So you see it's divided. So force is 9,000. Force is 9,000 newtons, which is option A. So I hope the idea is very, very clear and there is no confusion in this particular part, right? So now, after having the clear understanding of the second law, after having the clear understanding of how the second law is about the momentum change, and how the second law can also be represented as a impulse momentum equation, and how to deal with the word impulse in a much clearer fashion, now we can talk about the Newton's third law, right? Have a look at the Newton's third law now. So here it is, Newton's third law. So right now, it simply says that's a very popular one of the most popular laws of physics. It's almost a Hollywood movie dialogue. For every action, there is an equal and opposite reaction. And there are some quirks to it, that action and reaction forces, they don't act on the same body, right? For example, this is one ball, and if I take another ball over here, let's say like this, right? So these two balls are hitting each other, right? So if this ball and this ball, they are when these two balls are hitting each other, they are applying forces on each other, right? Let's say that if this ball is applying force of 10 Newton on this one, right? So this ball will also apply the force of 10 Newton on the other one. Action force and reaction forces are same, but action force acts on one body and the reaction force applied by this one on the other one, right? Reaction force is applied on the other body, right? So Newton's third law of motion is saying that whenever two bodies interact with one another, right, because force is a result of interaction. So Newton's third law of motion is saying that whenever two bodies interact, they apply forces on each other. That means whatever force is applied by the first body and the second one, that is the action force, will result in the same amount of reaction force, right? And action and reaction force, they do not act on the same body. One will get the action force and the other will get the reaction force, right? I believe the idea is very, very clear. Now, look into this situation. When you are trying to fire this cannonball with the help of this cannon, you see that this cannon, this cannonball is thrown outward, the action force, and the reaction force is acting on the cannon itself, due to which you have a recoil, and this cannon itself moves backwards, right? So action force acts on the ball in this direction, and the reaction force acts on the cannon itself in the backward direction. Same thing happens on this boat, right? Action force is applied on the boat in backward direction, and the reaction force is on the person in the forward direction, right? Same thing is on the rocket as well. As the rocket is creating the exhaust gases are creating a downward force like this, and the reaction of that exhaust is what pushes the rocket in the forward direction. Over here we have action and reaction forces. They are equal in magnitude, right? We know that action and reaction forces are equal in magnitude. Action and reaction forces act in opposite direction. Yes, it is true. Now let's talk about the next part. Action and reaction pair act on two different bodies. This is very, very important. Every action has equal and opposite reaction, right? So it will not happen that I'm applying the action force and I'm also going to receive the reaction force? No. Action force is applied on one body. For example, let's say that this is the wall, right? And I'm hitting the wall, right? So wall will experience the action force and I will experience the reaction force applied by the wall on me, right? So that's the idea, right? So magnitude of forces is same. Both the forces have the same magnitude, action and reaction. Direction of forces is opposite. So direction of force is opposite. So I'm applying the force on the rod in this direction, and the wall is applying the force on my hand in the opposite direction. I believe that is clear, right? Force for action and reaction pair, there is no need of contact, right? Right now, the nature of force was such, I had to make a contact with the wall so that I can apply a force on it. But if you talk about gravitational forces and all other forces, there is action and reaction going on, right? Like let's say that there are two bodies, right? Let's say these two masses are attracting each other, right? So in that case also there is action force and reaction force, both are happening at the same time, right? Same goes on for the magnets as well. So the action force acts and action and reaction force act simultaneously. It will not happen that action force is acting right now and the reaction force will happen after a certain time. They will happen simultaneously. They will act on each other simultaneously. All right. So now you have this thing called law of conservation of mass, law of conservation of linear momentum. Very important thing, right? And it's very important to understand the collisions of the body as well. Law of conservation of linear momentum. In the second law, you have seen the net external force acting on the body is rate of change of momentum of the body, right? A greater net force will change the momentum of the body much quicker, right? If we see that if the net external force is 0, right? If the net external force is 0, the rate of change of momentum of the body will be 0. The rate of change of momentum of the body is 0. That means the change in momentum of the body is also 0. That means the momentum of the body, the change in something is 0. That means that particular thing is constant. That means the momentum is constant, right? That means if there is no external force, then the momentum of the body will remain constant, or more precisely we can say momentum of center of mass of the body will remain constant, right? But it will only be true when there is no external force, right? So with the help of second law, we have just seen that, right? In the case of no net external force, the momentum of the body remains constant, right? So in the absence of external force, when the external forces can be neglected, in comparison to the internal forces, the linear momentum of the system of the particles remains same, or the momentum does not change, remain constant, right? So yeah, so these are all various things, right? And here it is law of conservation of linear momentum is there. So right now you see that the total momentum of the system remains same, rocket plus fuel. So whatever momentum the fuel has while moving backward, the same momentum is imparted to the rocket in the forward direction, right? So yeah, so whenever you talk about the gun and bullet, so whatever momentum was there, so initially the total momentum of the gun was 0, gun and bullet system, the total momentum of the system was 0. Right now, once you fire the bullet, so some momentum is imparted to the bullet itself, right? But the same amount of momentum, the same momentum is imparted to the remaining gun, right, in the backward direction, that you call as recoil, right? So overall system, when you talk about whatever momentum it receives in the forward direction, let's say 10 units, the 10 units momentum it receives in the backward direction, the total change in momentum is still 0. It was 0 before, it was 0 after as well for the system, right? So look into this question over here. There are two billiard balls, right, of mass 0.05 kilogram. They are moving in the opposite direction with 10 meter per second, right? There are two billiard balls, right, like this. They are moving in opposite direction. So this is the same direction, right? This is how the opposite direction looks like, right? So they are two billiard balls of same mass. So same mass is there, right? They are moving in opposite direction. Opposite direction. How fast? 10 meter per second. 10 meter per second. 10 meter per second. Okay. They collide and rebound with the same speed. They collide and rebound with the same speed. Okay. So if they were moving with 10 meter per second this way, after collision they are moving 10 meter per second the other way, right? They collide and rebound with the same speed. if the time duration of this constant is 0, right? If the time duration of the constant is t equals to 0.005, okay, seconds, then what is the force exerted on the ball due to each other? So this collision is happening in that small value of time, right? So what is the force, or we can call it average force, exerted by these balls on each other? Now, you know that here we are dealing with the impulse, right? So here we are dealing with the impulse in this situation. Right now, if you just think about it, when these bodies are about to come in contact, right now the force is 0. Now they are coming in contact, the force increases, peaks out, and now the force is reducing as they are moving apart, and as they move apart, the force becomes 0. So force is rising and then falling back to 0 again. Now, here you are talking about the average force again, we are dealing with the impulse. So the value of F delta t, average force into the time duration, is equals to the impulse, and impulse is nothing but change of momentum of the body, right? Change of momentum of the body, right? So right now, we have to talk about the force exerted by the ball on each other. So force will be delta P upon delta T. So what is the value of change of momentum? So we can say that when this ball, think about this ball only. So this ball was initially moving with 10 meter per second, right? And after the collision, the same ball is now moving in the opposite direction, 10 meter per second with the same velocity, right? So how much force has been applied on this ball? Whatever force is applied on this one, it will be applying the same force on the other one, action and reaction forces. So we can say that, first of all, calculate the change of momentum. Initially, its mass was m, right? So momentum is in this direction, and then the momentum is in this direction. The change of momentum is, mass is how much? 0.05. So 0.05 into 10, right? Final minus initial. So if you're calling this value as positive, the other value has to be negative. So minus 0.05 into 10. So you see that it is simply adding up. So 2 times 0.05 into 10. All right. All right. So final minus initial. So its momentum is a vector quantity. Remember that. So if that momentum is positive, the other momentum has to be negative. So whatever, right? So delta P is going to be 2 times delta P into 0.05 into 10. All right. And time is how much? 0.005. 0.005. That's it. Now you just divide it and you will have your answer, right? Now you just divide it and you will have your answer. Right now, the value of force you can get from this particular expression. That's it, right? So over here, you just divide it and you get the value of time as 200 Newton. That is your answer. Now you have one more question. Try to analyze it and solve it as well. Have a look at that. There are two bodies of mass 4 gram and 25 gram. They are moving with equal kinetic energies. The ratio of magnitude of their linear momentum is. Now, we are talking about momentum and kinetic energy. We are talking about momentum and kinetic energy. So understand that. Over here we can talk about, you see, kinetic energy or kinetic energy of the body is half mv square. Kinetic energy depends on m and v, right? And the magnitude of momentum also depends on mass and velocity, right? Okay. So if I simply multiply this expression by mass and divide that by mass as well, it will not change anything, right? But in the numerator, if I write it m square v square by mass, it will not, it's again the same expression, right? So m square v square is mv whole square. Mv is nothing but the magnitude of momentum, right? So in the numerator, it is the square of momentum upon twice of mass. This is the value of kinetic energy. So this is how you can relate the kinetic energy and momentum as well. A very useful expression that relates the kinetic energy of the body with the momentum of that body, magnitude of momentum of the body, right? So here you have it, kinetic energy and momentum, all right? It is kinetic energy is the square of momentum upon twice of mass. Now it is written, two bodies are there, 4 grams and 25 grams. They are moving with equal kinetic energy. So the kinetic energy is equal, right? And we have to find the ratio of their linear momentum. We have to talk about their momentums, right? So very easily we can do that. K1 is same as K2, right? So P1 square upon 2m1 is same as P2 square upon 2m2. Here the masses are given in grams, but whatever unit conversion factor you apply here, your same factor will be there as well and it will be cancelled out. So it doesn't matter, right? So P1 square upon P2 square is 2m1 upon 2m2, or 2 can be cancelled out directly, right? So we don't have to write it again and again. M1 upon M2. So P1 upon P2 is going to be under root M1 upon M2. Under root M1 upon M2. So 4 and 25, right? 4 and 25. So under root 4 and 25 is 2 upon 5. So this is the value of their ratio. So the answer will be option C, right? So option C has to be the correct option. Right, let's have a look into this particular part. So yeah, option C is correct. So this is pretty much everything about the part number 1. Now let's move ahead and talk about the second part, where we are going to discuss some more interesting concepts about the FBD and the constrained motion of the body. So let's have a look at those two concepts in very detailed manner, right? All right, so let us first talk about the concept of free body diagram. What do you mean by free body diagram? Let us first understand that with the help of a very interesting demonstration, right? So let's have a look at that. So here we have it. So you see that here we have a block, right? And this block is connected with a string, right? So right now what I'm going to do is I'll be applying a force on the block with the help of this string. So I'll be pulling this thing, right? And the block will start moving with a certain velocity, right? It will accelerate as I'm applying a force on it, right? So, okay, after a certain time, it will acquire a new velocity, its velocity will change, right? So here we are dealing with the effect of force on a single particle. Effect of force on a single particle. So I was applying a force. What will be the acceleration on the mass of the mass m, right? What will be the new velocity after a certain time? All those things we can talk about for a single particle. We have already done all that, right? But what happens sometimes, the force is acting not on one single particle but on a system of particles, like in this case. Here you see that here you have one block and then you have another block like this, right? And now if I start applying force like this, so right now I'm not only applying force on this single block, some of the force is also transmitted to the other block, right? So in this situation, I'm applying a force on system of particles, right? System of particles. I can also extend it to and include another particle like this. So right now I'm applying a force on 3 particles. So if the force is applied on a system of particles and you are interested in one of those particles, let's say this one, you are interested on this particle, like what are the forces involved with this particle only, right? So whenever we have a system of particles interacting with each other and we are interested in one of the particles of the system, then we have to talk about the free body diagram of that individual particle. So what does that tell us? Have a look over here. In a free body diagram, or in short we call it FBD, the object of interest. So here in these 3 particles, the object of interest is this one. This is the object of interest, right? The object of interest is isolated. So we will isolate it from the system, right? And in its surroundings, and the interactions between the object and the surroundings, the interaction between the object and surrounding, that is the forces involved, right, are represented in terms of forces. So what are the forces involved in this picture? On this single object, we will talk about only those forces that are involved on this one, right? We will not be discussing the forces that are acting on this one. We are not discussing the forces acting on this one. When we are talking about this particle, we are only concerned with the forces acting on this particle. So that will become the free body diagram of this particle if we are only showing the forces on it, right? So yeah, this is the idea. We will also draw the free body diagram of various situations. Let's have a look at that. So here we have it. Let us put these things aside and let's have a look at these situations. So when we are going to draw the free body diagram, we'll be drawing the FBDs in different situations, and in those FBDs we will be involving one of these forces, right? So to be able to use these forces and draw a successful or meaningful free body diagram of a body, we need to understand each of these forces in great detail. So let us understand each of these forces, each of these terms in a very detailed fashion, right? So first term is weight. What do you understand by the weight? So my dear kids, weight is nothing but the force by which the earth attracts the body toward itself. So here I have this particular mass. This mass is hanging from the body, from a certain point, and now the earth is attracting this mass toward its center. So the weight of this particular body is m into g. That is the force by which earth is pulling this body toward its center, right? Okay. So the weight is the force by which the earth pulls the body towards its center. The earth pulls the body towards its center, towards itself or toward its center, whatever, right? So if the body has a mass m, then the weight of the body will be m into g, right? So what is the weight? It's a force by which the earth is pulling the body toward its center. It is m into g, and the unit is going to be, of course, newtons, right? Now, what is a normal force? Normal force. So normal force is a type of contact force, right? Whenever two bodies are in contact, right, then this force may come into the picture, right? Understand that. For example, let's say the weight of this body is 50 Newton, right? And if I drop it, it will start falling like this, right? Now, if I apply a force more than 50 Newton, right, the downward force is 50 Newton. If I'm applying a force more than 50 Newton, the body will start rising up, right? And if I'm applying a force less than 50 Newton, let's say the downward force is 50 and I'm only applying 40 upwards. So it will start moving downward, right? Yes or no? Okay. But if the body is being pulled towards the earth by the force of 50 Newton, the weight is 50 Newton, I'm also applying 50 Newton in the upward direction. So this body will neither move up nor it will move down, right? Now the same situation is happening when the body is placed on the table. Let's say that this is table and the body is placed on it, right? So right now the table is providing that force that is keeping the body wherever it is, and the body is neither moving up or down, right? So that force which is coming due to the contact between these two bodies here is the normal force, right? So yeah, this is the normal force, okay? Normal force. So normal force will be applied by the contact surfaces to this particular body like this. Now the normal forces will also come into the picture in various situations. For example, we have one block like this, another block like this. So you see that whenever you are pushing the block, this one, right, let's call this force is F, right? These two bodies are in contact over here at this surface. These two blocks are in contact over this surface, right? So they are pushing against each other. When they are pushing against each other, they are also applying the normal forces on each other, right? So normal forces are applied when two bodies are trying to press against each other. I am standing on the ground. Am I pressing the ground? Yes. So the ground must be applying a normal force on me, and I am also applying some force on the ground, right? Because the force is always an interaction, right? Here in this situation, again, when I have two block system, right? So right now I am applying some force, let's say 20 Newton on a bigger block, right? So in this situation, what will happen? These bigger block and a smaller block are also in contact, and are they pushing against each other? So as soon as I start applying the force on a bigger block, these two blocks also experience a force in between, right? And the force that is pushing each other, the surfaces are pushing each other, that force is the normal force between them. If I include another block like this, right? If I include another block like this into the picture, right now what is happening? If I push the bigger block over here, so what is happening? Let's say I apply a force of 100 Newton on the bigger block, right? So what is going to happen? The force of 100 Newton is acting on the bigger block, but some force due to that is acting between these two surfaces, because these two surfaces are also pressing against each other. These two surfaces are also pressing against each other as soon as I start pushing this one, right? So in that situation, the normal forces start acting between the surfaces as well, right? Now, since I'm not pressing each other right now, so right now there is no normal forces between them. Of course, the normal force is there between the surface of the surface of the table and the body, right? So the normal forces are between the table and the body itself. But right now there is no normal forces between them, right? It's because nothing is pushing them. They are not pushing against each other, right? But as soon as I start pushing them and the surface has some friction on it, so now what is happening? There is a normal force acting between them. So yeah, this is it. So right now you see that, just understand this idea. Whenever surfaces are pushing against each other, in that situation, the normal forces will come into the picture, right? Okay. The next thing is tension force. Tension force is basically a kind of pulling force, right? So you see that whenever we are going to have a string, right? Imagine that we have a mass over here, right? And it is connected with a string like this. So what is going to happen? Let me just take this part like this. So what is happening? This mass is hanging from here, right? So the weight is acting, the weight of the body is pulling the mass in the downward direction. That force is acting on the mass in the downward direction, mg, okay? But if you just focus on the rope itself, right? This rope is pulling the hand in the downward direction, okay? And this rope is pulling this particular end in the upward direction. And to demonstrate it, you can also have a look at an elastic band kind of situation. So imagine that instead of this rope, I had an elastic band. And if I'm trying to stretch it, what will happen? This end, let's say I have one hand over here, another hand over here, and I have a elastic band over here, right? So when I'm going to stretch it, what will happen? This hand will feel a pulling force in that direction. And when rope is stretched, right? When the band is stretched, this hand will experience a pulling force in the upward direction. So what will happen? Right, here you can see that whenever I have a rope or a string like this, it is connected to one end over here and another end over here. So the nature of the forces, the nature of tension force is such that this end experiences a force in this direction, and this end, whatever is connected to the other end, will experience a force in the upward direction. So this will happen, right? Okay. So this is the nature of tension force. It pulls everything that is connected on the ends like this, right? So then the next thing is frictional forces. This is also a type of contact forces. If the bodies do not make a contact, there is no friction possible between them, right? We will also talk about the friction force in detail in the third part. And then we have the elastic spring force. So elastic spring force is also there whenever we have the compression and expansion of the spring is going on. So right now we have this thing is going on. So elastic spring force. So you see that if you apply the force on the string beyond a certain point, so you see that the spring will not get back to the original shape. Rather what happens, it is, if you leave it, it does not go back to the original shape. There is a permanent deformation in it. But if you try to make the spring back in the normal place. Now, if you apply a smaller force and you leave it, the spring goes back to the original condition. That is the elastic spring force. We are talking about that, right? So we'll be dealing with that as well in some parts. So these are the forces we are going to deal with when we will draw the FBD of one of the particle involved in the system, right? Okay, so let's move on and talk about the next idea. Okay. So weight we have discussed, right? The force by which the earth pulls the body toward itself. Normal force, whenever two bodies are in contact, right? They apply a force on each other. That is a normal force, right? It's a contact force, and it is only applied when two surfaces are pressing against each other. If the surfaces don't press against each other, then the normal force will not be there. If there is any possible situation when the surfaces seem to push against each other, they will be applying the normal force. If I push against a wall, there is a normal force between my hand and the wall, right? Okay. So yeah, normal force is there, right? Tension force. We have also seen that tension force, when a rope or a string is stretched, the force is developed in the rope. It is called as tension force. The nature of tension force is such that it is always a pulling force by nature. So whatever is connected at the ends of the rope, it is always pulled. It is always pulled, right? Okay. So this is how the tension force is represented. This is not the force on the rope, right? This arrow is not representing the force on the rope. These arrows are representing the nature of the tension force, that it is going to pull the object number 1 in this direction, and the tension force created in the rope is going to pull the object number 2 in this direction. This is the nature of the tension force. It pulls everything connected towards the ends like this, right? So yeah. And the next thing is frictional forces. So whenever two bodies that are rough, they have a relative motion between them, right? So if I have this surface, that is a rough surface, and my other hand is also rough, right? So if these two things are moving together, there is no relative motion and no concept of friction will be there. But when two rough surfaces have relative motion, you see that now the other surfaces can feel the other surface moving over it, right? So now what is happening? There is frictional force involved between the surfaces, right? Now the next thing is elastic spring force. So as I have already told you that if I have a spring, right? So if I stretch the spring from its original position for a displacement x, let's say, right? So what will happen? The spring will apply a restoring force, that is k times x, right? So more stretching I provide, more restoring force the spring will provide back, right? And it will only happen till a certain limit. Beyond a certain point, if I stretch the spring won't be able to get back, it will fail, and that is why we call that limit as elastic limit of the spring, right? So we are dealing with the elastic spring force, right, which is F equals to kx by magnitude. Minus sign is representing that displacement is in this direction, the force is going to be in the opposite direction, right? This is it. So the next thing is this. Okay, so over here we have this situation going on, translational equilibrium. What do you mean by translational equilibrium? Whenever we talk about translation of a body, that means a body is shifting from one place to other place, right? If I'm talking about the translation of this body on the table, so what is happening? Body was originally at this place and you applied the force on the body, and now the body is at a new location. The body has translated from this place to this place, right? So this is the translatory motion. Now equilibrium means the state of motion should not change, right? In the translation, the body has no tendency to rotate, right? When the body is under translation, the body has no tendency to rotate, right? That means no torque, no momentum is involved in this situation, okay? So translatory equilibrium, in the translational equilibrium when we talk about, this part, what can we say, right? In this situation, in the translational equilibrium, we don't want any acceleration, right? The acceleration has to be 0. And acceleration is 0, that means the net force has to be 0. So in the translational equilibrium, we want the body to translate without any acceleration. That means the force in all directions should be 0. So Fx, the net force in the x-axis should be 0. The net force in the y-axis should be 0. The net force in the z-axis should be 0. So in that situation, we call it a translational equilibrium, right? Okay. Thus, if a body is under translational equilibrium in a particular frame of reference, it must have no linear acceleration, right? So that's what I said. In the translational equilibrium, we don't want any acceleration in any possible direction. So when it is at rest, it is under static equilibrium, right? When the body is at rest, right, under the influence of external forces, you are applying a lot of forces on the body, but the body is not moving. That is the case of static equilibrium, right? When it is moving at a constant velocity, then also the state of motion is not changing. Body is moving with 20 meters per second. If there was a net force acting on the body of 5 Newton, the body's velocity will not remain 20, it will change. There will be some acceleration. So if you apply, let's say 5 Newton force and still the velocity is not changing, that means that 5 Newton is being cancelled by some other force that is also equals to 5 Newton, right? Yes or no? Otherwise the body will have a net force, and that's why an acceleration. So we have a dynamic equilibrium. Dynamic equilibrium means a body is moving at a constant velocity and all the forces are cancelled out, right? So static equilibrium, body is stationary and all the forces are cancelled out. There is no motion is going on. And dynamic equilibrium means body is moving at a constant velocity and all the forces are being cancelled out, right? But the word equilibrium is telling you that there is no linear acceleration in the case of translational equilibrium, right? So conditions for translational equilibrium, as I said, the net force in all direction must be 0, right? That is Fx should be 0, Fy should be 0, Fz should be 0. Okay. Have a look into this situation, right? So the question is saying that a block of mass 30 kg is suspended by 3 strings as shown in the figure. Find the tension in each string. So you have one string A, another string B, another string C. You have to find the tension in each string in this particular case, right? So what can you do for this? We can say that in this situation, all the strings are under tension because of this weight that is hanging off it. So the mass is 30 kilograms. So the weight that is hanging over here is m into g. So 30 into g, which is 300 Newton, right? So that's why it is written 300 Newton by default. Okay. So find the tension in each string. So needless to say, how can you draw the arrows of the tension? No need to worry about that. So the nature of the forces or the tension of this string is such, it will pull this end in this direction and it will pull this end in this direction. Similarly, the tension of this rope will pull this end in this direction and this end in this direction. It will pull this end in this direction and this end in this direction, right? Okay. So now if you try to separate it like this, so what is happening? This is A, right? Look at this. This is B and this is C. All right. So this is how it is happening. This is 37 degrees, right? Okay. This is 37 degrees. So do not get afraid of that 37 degree, right? Let me tell you a small trick for these angles. So if you have this thing going on, this side is 5, this side is 3, the angle between them is 53, right? So the remaining angle is 53, this is 90, the remaining angle is of course 37, okay? So this angle is 90, the other side is 4, right? So this is the triangle on which this 37 and 53 are there, right? So if you want, you can write down the values of cos 53, sin 53, cos 37 and sin 37 from here in this triangle. Okay, so no need to worry about that. So this force is the tension force over here, tension in A, this is the tension in B, and this is the tension in C. All right, this is the tension in the rope C. Good. So I hope the idea is very, very clear. So tension in the rope C is how much? We can say, look at the free body diagram of this body. So you see, free body diagram of this body is telling you that the upward force is tension in the rope C and the downward force is mg, right? So by looking at the equilibrium in this direction, because the whole system is under a static equilibrium, that means every particle must have no net force, right? So that means there is no net force in this direction. So whatever force we have in the upward direction must be balanced by whatever force we have in the downward direction. So Tc is equals to mg. Right? So we have mg, which is 300, 30 into 10, which is 300. So Tc is 300 Newton, you can write it. Okay. Now you can see that the components of Tb can be taken in this direction as well as in this direction. So for the components, let's take a different color, right? So this angle, or you can call this one, this is 37, so this is also 37. Right. So just to show you in an easy manner, this component is Tb cos 37 and this component is Tb sin 37. Yes or no? So in this triangle, what is cos 37? What is sin 37? Cos 37 is 4 by 5 and sin 37 will be 3 by 5. No problem with that, right? You know. Yes. Okay. I believe the idea is very, very clear. So in this situation, you can just balance it out. So right now, you can balance the force in this direction. So this force, Tc, is balanced by this force, Tb sin 37. So no need to worry about that. So Tb sin 37. Sin 37, you can put the value directly from this one. So as I said, sin 37 is going to be 3 by 5. So Tb sin 37, that is same as 300 Newton, right? So you see Tb is equals to 500. So the tension in the rope B is 500 Newton. Now, balancing the force in this direction, you can say that Tb cos 37 is equals to Ta. So Ta equals to Tb cos 37. Tb you have just calculated 500 and cos 37. Cos 37 is 4 by 5. So you have 400 Newton. So I hope the idea is very, very clear. You have all the values in front of you. You have Tc, which is 300 Newton, the tension in the rope C. You have Tb, which is tension in the rope B, which is 500 Newton. And you have Ta, tension in the rope A, which is 400 Newton. I hope the idea is very, very clear. And there is no confusion around it, right? Now, in the previous numerical, we had, the system was stationary. Nothing was moving in the system. And we had to calculate the forces. So we said that it's a case of a static equilibrium and all the forces must be balanced. Here we are going to see the dynamics of the particles. So translational motion will be there, but the particles will be moving right now like this. So here particles are moving. So right now you see we are dealing with the dynamics of the particles. So translational motion of accelerated bodies. So right now what is happening? We are applying force on a system of particles and the whole system is under some external force, right? So the net force is not zero. So the whole system will be under some acceleration. Okay, so equilibrium is not there, right? We are done with the equilibrium, right? So whenever you have to deal with the problem of equilibrium, you will form the equation. You will say sigma fx is 0, sigma fy is 0, sigma fz is 0, and you can solve it. That kind of problem will be there. But if the net force is not 0, so what is going to happen? We will have a dynamics of particles when they are accelerated. The particles are moving. So you see that this system is there. We have a system of two particles that is under the influence of external force, and the whole, because the net force is not 0, the whole thing will be accelerating under the influence of net external force, right? Now, very interesting thing will happen. Just have a look into this situation. So just deal with the two bodies as of now. Okay, just deal with two bodies as of now. So right now what is happening? Here I have body number 1, body number 2, and I'm applying a force on this body like this, right? So think about it. Are these two surfaces pressing against each other or not when I'm pushing the bigger body? So we can say yes, when you are pushing the bigger body, these two bodies are also going to push each other. Since these two bodies are pushing against each other, and as I have told you, if two surfaces are pressing against each other, there will be normal reaction between them. So will there be normal reaction between them or not? So I will say yes, there will be normal reaction or normal force between them as well. Okay, so the normal contact force between them will act, that is not visible, but there will be a normal force as well because they will be pushing each other. So we can show that like this, right? So you have separated it, right? You have separated it. It will apply normal force on this one, and same normal force will be applied on the other one because it's an action reaction pair. If I'm pressing against the wall, let's say I'm applying a force of 50 Newton on the wall is also applying a force of 50 Newton on me, right? So here, if these two surfaces are pressing on this particular surface, right? So whatever force is applied by M1 on M2, same is applied by M2 on M1. So let's call that normal reaction is N1 or N, right? So you see that on this side we have this normal reaction pressing each other, okay, right? Now the whole system will be accelerating with a common acceleration A. The whole system will be accelerating by this force with a common acceleration A. So that is shown over both of them, right? This force was only acting on the smaller body over here. So this force, when we are drawing the free body diagram, we cannot show this force acting on the other one as well. The other one is only experiencing the push applied over this surface, right? The other one is only experiencing this push applied the surface, while the first one is experiencing both of them, F and N, okay. Now you can draw the free body diagram. You have drawn the free body diagram of both the surfaces. Now you can analyze them, right, separately. Now you can analyze them separately. And to analyze the bodies separately, we have these equations. You see that this is the first body, right, experiencing the force F and N, right, and the second body is only experiencing the force that is acting on this surface, right. You see that the force which was acting over here is not acting on the second body, it is only acting on the first one. So the first one is experiencing this force as well as the reaction force over here, and the second body is only experiencing that contact force over here. Right, so right now these are the forces. These are the free body diagrams of both the bodies, right? Both of them are moving with a constant acceleration A like this, right? So for the first one, when you analyze the motion of the first one, you see F minus N, the net force, is mass times acceleration. So M1 into A. This is the first equation. For the second one, N equals to M2 into A. This is the equation for the second one, right? N equals to M2 into A. So these are the two equations. You can just add them up and get the net value of force, which is this M1A plus M2A. From here you can get the value of acceleration, which is force upon total mass, force upon M1 plus M2, right? So you have net force upon total mass. This is the value of acceleration of the body. I hope the idea is very, very clear. Now the next idea is, Now the next idea is, what will be the value of normal reaction? So you have already seen that normal reaction is m2 into a, and the acceleration you have calculated already, f upon m1 plus m2. So you can just put the value of a over there. So m2 into a is f upon m1 plus m2. That's it. So normal reaction will be m2 upon f, m2 into f upon m1 plus m2. That's it. So this is the idea, right? You can similarly discuss the motion of three bodies, right? So here you have the three body system is going on for you. So here you have it. So yeah. So right now you have a three body system. You have one body, second body, and the third one. And one of them is experiencing the force. So this one is experiencing the force over here. Right now, I'm not applying any force on any of them. So these surfaces, this surface, they are not pushing against each other, right? But as soon as I start pushing the surface from here, you see that now the surfaces are also pushing against each other, right? So now there is a contact force. As long as I'm pushing it, there is a contact force between the surfaces, right? Now, the contact force at this surface, we are calling it N1. So N1 is acting here and on the other one. On this surface, the contact force is N2. So N2 is acting on this one as well as on this one, right? So now let us put it aside and try to analyze the motion of these three bodies as well. So let us first separate them and try to mention the forces acting on each one of them by drawing the FBD of every single particle, right? So here you have it. This is the first particle. It is experiencing force F and the normal contact force like this, N1. And the whole thing is moving with the acceleration a. So this one, this one, this one, all three of them have a same acceleration a. So yeah, F, N1 and the acceleration a. That's what we can show for the first one. This is the FBD of the first one. For the second one, it is experiencing a normal reaction N1 and N2. So N1 and N2 and the acceleration a. The force is acting on this body only and it is not acting on the surface of the second body. We cannot show it in the FBD of the second one. Same we can go for the third one and draw the forces acting on the third one, right? So when we do that, and now we can analyze it. So you see that the net force F minus N1 is M1 into A. This is the first equation, right? Similarly, for the second equation, N1 minus N2 is M2 into A. This is the second equation, right? And for the third one, N2 equals to M3 into A. This is the third equation, right? So you have these three equations happening, for yourself. You have these three equations working for you, right? And now you can just go ahead with them and talk about it. So just add them up, and by adding them up you can get the value of acceleration. Normal reactions are cancelling out and the value of acceleration is force upon total mass, F upon m1 plus m2 plus m3. This is the value of force that you are getting into this situation, right? Okay, so acceleration you have calculated. So when you are applying the force F on this system, the acceleration is net force upon total mass, net force upon total mass, m1 plus m2 plus m3. I hope the idea is very, very clear. Now, net force upon total mass. Now, similarly, you can get the values of contact forces N1 and N2 with the help of the equations that we have just seen. The contact forces N1 and N2, then, values of N1 and N2, the normal reactions that you are getting at this surface as well as this surface, you can get from these equations. By solving these equations, you can get the value of normal reactions, right? So by looking at N1, just put the values in equation, and in that equation put the values, right, and solve it. So by looking at the values of N1 and N2, you will have a very clear insight, right? N2, let me draw the diagram for you so that you can understand it in a much better way. So this is M1, M2, M3, right? Normal reaction N2 is acting over here and normal reaction N1 is acting over here, right? Okay. So N2 is F is the total force, F into M3 upon total mass, right? F into M3 upon total mass. So normal reaction N2 is acting at this place. So the mass ahead of at this surface, mass ahead of this place where the N2 is acting is only M3, right? Mass at this intersection is only, mass ahead of this intersection is only M3. So F into M3 upon total mass. What is normal reaction at this surface? We can say F mass ahead of this intersection is M2 plus M3 upon total mass. You see that? F mass ahead of the intersection M2 plus M3 upon total mass. Look at this thing one more time. Very interesting observation you can see, right? Here we have to talk about the value of normal reaction at two very crucial intersections, right? So focus over here. We have the first intersection over here. Ahead of this intersection, you have only the mass m3, right? So the normal reaction at this intersection is F total force, the external force, F into m3 mass ahead of this intersection, F into m3 upon total mass. When you talk about normal reaction at this intersection, so ahead of this intersection, we have two masses, m2 plus m3, right? So mass ahead of this intersection is m2 plus m3. So the normal reaction at this one is F times m2 plus m3 upon total mass. F times m2 plus m3 upon total mass. Similarly, by looking at this observation, if you have a more complicated multiple particle system, you can get that as well. So now this is the idea. You have now a two particle system. And right now what you need to do is two blocks are of mass 4 kg and 6 kg. They are placed in contact with each other on a frictionless horizontal surface. Okay. So the mass is 4 kg and 6 kg. Okay. And if we apply a push of 5 Newton on the heavier mass, so this is 6 kg and the other smaller one is 4 kg. You are applying a mass of 5 Newton on a heavier mass. The force on the higher mass will be, the force on the lighter mass will be. So the lighter mass is going to experience the normal reaction only, right? The lighter mass, the force on the lighter mass is going to experience the normal reaction. Let's call it N, right? So we need to calculate the value of normal reaction basically. Yes or no? So first of all, we will talk about the FBD of individual particles. So if I try to draw the FBD of this smaller particle, it is only experiencing the normal reaction and that causes the acceleration. So normal reaction is m into a, right? Normal reaction is m into a. So what is the acceleration, right? Mass is 4, acceleration is force upon total mass. Force upon total mass, 6 plus 4, which is 10, right? So that's it. That is the normal reaction. That is the force it is going to experience. So 4 into 5 upon 10. So 2 Newton. So answer will be C. C will be the answer. The second particle will experience a force of 2 Newton in this situation. I hope the idea is very, very clear. Right. So yeah. Look into this situation. We have two blocks. They are in contact on a frictionless surface. One has a mass m, the other has a mass 2m. M and 2m. A force F is applied on 2m. Okay. The force is applied on 2m. Okay. Now the same force F is applied on the mass m. Okay, so in the first case, force is applied here, and the second case, the force is removed from this side and applied from this side. Okay. Now, in these two cases, what will be the ratio of contact forces on the contact surface? Okay. In the first case, when you apply the force here, you will have some contact force here, and when you remove the force from here and apply from here, you will have another contact force over this one. So you have to take the ratio of those contact forces. So let's take the case 1 here. Right, you have the mass 2m and mass m like this, and you are applying the force F. You are applying the force F on here. All right, you are applying the force on this side, right? And it is placed on the surface. Now think about it. This is 2m and this is m. Now, if you try to draw the FBD of the whole thing will be accelerated by the acceleration A. So the FBD of this thing will look like this. Just to show you, like once you practice enough, you can solve these questions without a lot of, pen, right? So you see that this is how you can draw the FBD of both the bodies, right? Okay. Now, in this situation, when you need to talk about the normal reaction, so what will be the normal reaction? We can say N equals to m into A. M into A, and what is A here? A is force upon total mass. So force upon total mass. M plus 2m is 3m, right? So m and m we can cancel out from this side, and F upon 3 basically will be the final value of normal reaction like this. Okay. Now in the second case, case number 2, when we have body of mass 2m here and a body of mass m here, and a force is applied from this side In the first case, force is applied on this side. In the second case, force is applied on the other side. Now, when we do that, the FBDs are drawn like this. So M is here experiencing a force like this. Normal reaction is acting on this one is like this. The normal reaction on the mass 2M is acting like this. Okay. So that's it. And both of them have a common acceleration A. All right. That is complete FBD. So right now we talk about N. So N equals to, what is N? N equals to M2M into A. Yes or no? 2M into A. Right. So what is A? A is force upon total mass. Force upon total mass, which is 3M. So it is 2 times F upon 3. So I hope the idea is very, very clear. Let's call the normal force in the first case as N1. And let's call the normal force in the second case as N2. Right. We have to find the ratio of normal force in both the cases. So N1 upon N2 you have to find out. So N1 upon N2 you will have N1 upon N2 you will have like this. So F upon 3 and 2F upon 3. F upon 3 and 2F upon 3. So this and this cancels out, this and this cancels out. So 1:2 is the final answer. That is the final answer. 1:2 will be the ratio of the normal reactions. That's it. 1:2 is the answer. So option B is correct. I hope the idea is very, very clear. This is how you deal with the problems like this, right? No problem with this one. And now look at this particular question. We have two blocks of masses 1 kilogram and 2 kilogram. 1 kilogram and 2 kilogram. They are experiencing the force of 6 Newton in the first case like this. In the second case, the force is like this. Okay. Find the force of interaction of the blocks. So we have to find the normal reaction at this surface over here and at the surface over here. Very easily you can do that. Normal reaction at this surface is going to be F into, right, F into mass ahead of that intersection, which is 2 kilogram, right, upon total mass 1 plus 2, which is 3. So it is only 4 newtons, right? And in the second case, what will be the normal reaction? We have F into mass ahead of the intersection, which is 1 upon total mass, only 2 Newton. So I hope the idea is very, very clear. In the first case, 4 Newton will be the normal reaction, and in the second case, 2 Newton will be the normal reaction in this situation. You can also do the same way. You can draw the FBD of individual parts and do that. So here I have just shown you the trick that I have shown you in the previous case. That also works here as well. Yeah, so let's move on and talk about the next idea. So 4 Newton and 2 Newton is the answer. Now the next thing is, two bodies are connected with a string. So in the previous case, the bodies are touching each other. So we push one body, these bodies push against each other, and that in turns create the contact force. And here what is happening? We have two bodies, they are connected with the help of a string, and now you are trying to pull the body, pull one of them with the external force F. So what will happen? As soon as you pull one body with a force F, the rope will get under tension, and since the rope is under tension, it will pull its ends like this, because that's the nature of the tension force, right? It is pulling the end like this. So see that the mass M1 is experiencing a tension like this. So if you separate it, mass M1 is experiencing a tension like this, and the second mass M2 is experiencing a tension like that. It is experiencing tension like that, and that is the value of acceleration shown in this situation, right? Now if you draw the FBD of these bodies independently, right, this is how you can draw it. So for the first one, F minus T is M1 into A. This is how you can draw it. And the second situation, you can draw T equals to M2 into A like this. T equals to M2 into A like this, right? So by analyzing both of them, you can get the value of force, right, like this. Yes or no? So it is acceleration, you can get that force upon total mass, just like the previous situation, right? So acceleration is force upon total mass like this. So total force upon net force upon total mass is the acceleration. And what is the tension in the string? Just like the normal reaction you calculated, you can calculate the tension in the string as well. So by putting the value of acceleration, tension was M2 into A. So A is F upon M1 plus M2, just put it. You will get the value of tension in the string as well. Now look at this situation and try to solve it. We have three blocks of masses 2 kilogram, 3 kilogram, 5 kilogram. We have masses 2 kilogram, 3 kilogram, 5 kilogram. Right, they are connected to each other with a light string, and then it is placed on a frictionless surface as shown in the figure. The system is pulled by a force of 10 Newton. Find the value of tension in this thing. This is T1, this is T2. You have to find the tension in the first string, T1. So very easily you can calculate that. So the trick says that tension, just like the normal reaction, you can apply the same trick over here as well. So with the help of the trick you can solve it, and with the normally you can also solve it as well. So tension in the first one is going to be total force into mass ahead of the interaction point, which is 3 plus 5 upon total mass, 2, 3, 5. That's it. If you follow that small trick, you can do these kind of problems very, very easily. So you have 10, 5 and 3, 8, and 2, 3, 5, 5, 5, 10. So you have 8 newtons. Option C is correct, right? Option C is going to be correct, right? And now if you want to follow a normal pattern, you can do that normally as well. Acceleration will be total force upon total mass. So net force is 10 Newton and the mass of the entire system is 2 plus 3 plus 5, 10. So acceleration is 1 meter per second square, right? And by analyzing the FBD of any one of them, so you see that when you are dealing with tension force T1, look at the remaining system as one system. You can do that as well. So you have the remaining system as it is. T1 is there and the rest of the system is there. So T1 equals to mass of this system into acceleration. So 5 plus 3 into A. That's how you can solve it as well. T1 is 8 Newton. So no need to worry about that. You can also solve it by making equations and invest a lot of time. But you can solve a lot of problems and find a pattern. And by looking at the pattern, you can always solve the problems much quicker, right? Okay. So here it is. All right. So now you have the pulley block system, very popular, but not very difficult here as well. So here you see, we have two pulleys and we have a pulley and two masses are attached to the end of the pulley, M1 and M2, right? So what is happening over here? The M2 being heavier is moving downward with the acceleration A. Same M1, it is connected with the inextensible string. So whatever acceleration is there in the downward direction, this thing will have the same acceleration in the upward direction. Right, so it also have the same acceleration A, right? So what will be the net acceleration? Net acceleration will be net pulling force upon total mass. So you see that M2G is acting downward. Here M1G was pulling downward. So what is the net force? M2G minus M1G, right? That is the net force that is pulling downward, the taking system downward upon total mass is going to be the net acceleration, and the tension in the string will be 2m1 m2 upon m1 plus m2 into g. You can also solve it, right? Take the FBD of individual bodies, right? Take the FBD, T is acting this way, m2g is acting this way, m1a is acting this way, and on this one T is acting this way, m1g is acting this way, A is acting this way. Make two equations and try to solve it. You will also get the same two values, right, for acceleration and tension. Okay, now have a look into the situation and try to solve it as well, right? Have a look into the situation and try to solve it as well. So the question is saying that, my dear kids, that two masses M and M, right? Two masses M and M, they are attached to a string which passes over M1 and M2, I should call it, M1 and M2. They are attached to a string which passes over a frictionless smooth pulley where M1 is 10 kilogram and M2 is 6 kilogram. M1 is 10 kilograms. And M2 is 6 kilograms, right? M1 is 10 kilograms and M2 is 6 kilograms, right? Okay. Now what is happening? The acceleration of the masses is going to be, what will be the acceleration of the mass? So as I've already told you, acceleration of the mass you can easily calculate, right? Acceleration of the mass you can easily calculate. Net pulling force, which is 10 into G, 100. Let's take the value of G is 10 into 10 into G, M2G minus M1G minus 6 into 10, which is 60, upon total mass, 10 plus 6, 16, right? That's it. So you have 40 upon 16, 2.5 meter per second square, right? This is the equation we have applied. Acceleration is m2g minus m1g upon m1 plus m2. So m2 is given as 10. So 10 into 10 is 100. m1 is given as 6. 6 into 10 is 60. So 100 minus 60 upon 10 plus 6, which is this, right? So yeah, 2.5 meter per second square. Option C is going to be the correct option. So yeah, this is it, right? So I hope the idea is very, very clear. Right, that's pretty much everything about this particular part. Now let us move on and talk about the next idea and understand few more concepts, okay? So far we have seen how to get the acceleration of a body or how to get the parameters of a body when the whole system was accelerating with a common acceleration. So far we had bunch of blocks and all the blocks were experiencing a force from one side. So all the blocks had a common acceleration and we did some problems on those type of situations, right? But now it is also possible that systems are connected, the particles of the system are connected each other, but the acceleration of individual particle is not same, right? Which is we are going to see in a few seconds. So in that situation, how will you relate the parameters of the motion of each and individual particle? How will you do that? In that situation, you need constraint equations. So what is constraint equations? How to use it? Let us understand that now in a step-by-step manner. So have a look at that, right? So far we have seen, understand, why are we learning constraint equation? So far we have seen if you have a body like this, one particle, if you have a system like this that has two particles or three particles that is experiencing a force, let's say like this, then every particle of the system is accelerated by a common acceleration a, and then you can solve it, right? But what I'm telling you that it is also possible that particles of the system are connected with each other, but the acceleration is not same. And the simplest case of that was a simple simple pulley system, right? So here you have one pulley and here you have another pulley and the block. One pulley and the block and then another block. So this is the mass M1 and this is the mass M2. So if M2 is heavier, this will go up and this will go down. This will go down and this will go up. So you see that the acceleration of these block is not going to be same because acceleration is a vector. If the second block is accelerating with an acceleration in the downward direction, the first block will accelerate with the same magnitude but in the upward direction. So if the acceleration of M2 is A, acceleration of M1 will be minus A. So you see that here two particles are there in a system, right? But they don't share the same acceleration. They have different acceleration. We will also look at a much complicated case of this sort, right? And we will try to find what will be the acceleration of two particles that are forming a system, right? Then we can also have a 3-particle system and 4-particle system and multiple particle system. But for the NEET preparation, we will limit ourselves to the two-particle system, right? Because this is what we say, what we see in the previous years. So here it is. Now, so far we have seen acceleration in this situation is total net force upon total mass of the system m1 plus m2. So acceleration comes out to be force upon m1 plus m2, right? This is what we have seen. No problem with that. But now there are situations, there are going to be situations like this, let's say like this, right? Here you see that the particles are connected. You see this particle number 2 and this particle number 1, they are connected with each other, but they don't share the same acceleration. So how to calculate that? We can get the relation of acceleration and velocity of these particles with the help of constraint equations. Let's understand how to use it. What do you mean by constraint equation? Constraint means to be connected with something, right? So here you see the motion of first and second is not independent. The motion of these two particles is not independent from each other. If you move the first block, the second block will move on its own, right? Or the first, if you pull the first block, second block has to follow that motion. Or if you move the second block, first block has to follow that motion. So we can say that motion of any one of them is connecting or dictating the motion of the other block. Similarly, in the second case as well, even if we have multiple pulleys here, if you move the first body, the second will move as well. So you see that the motion of the particle is connected with each other, right? But however you want to move it, there is a limit to it. That is, the total length of the string is something that is a limiting factor, right? You cannot move the block by 50 kilometers in one direction if this string itself is of 2 meters, right? If this string is, let's say, total string length is 2 meters, you cannot move the block 1 for 50 kilometer displacement, yes or no? Because you are limited by the length of this string, yes or no? So here we can do it. Let's understand this part, right? So let's say that if the length of this side of the string is x1 and if the length of the other side of the string is x2, so we can say that one thing is for sure, or one constraint is there that this system has to follow, and that constraint is, my dear kids, is x1 plus x2 is the length of the string, and this length of the string is constant. X1 may change during the motion, X2 may change during the motion, the block is moving up or down. So X1 and X2 will change independently, but what will not change is the total length of the string. So this constraint is something that is dictating the motion of these two individual particles. Yes or no? Right. Now, you know that if you differentiate displacement, you get velocity. So if you differentiate how x is changing, x1 is changing, you get the velocity of particle 1. If you differentiate x2, you will get the velocity of second particle. So differentiate it. So on differentiating, you will get dx1 by dt1. You will have dx1 by dt1, which is velocity of first particle. Again, differentiation of x2 will get velocity of second particle, and L is the total length of the string, which is the constant, and differentiation of constant is 0, right? So from here you can say the relation between the velocities of these particles is v1 equals to minus v2. So this is what we can think about, think in terms of common sense as well. If the first particle is moving with velocity v1 like this, the second particle has to follow the same velocity but in the opposite direction. And if you differentiate this relation further, so v1 and v2 can be differentiated further. v1 is the velocity of the first particle. Differentiation of v1 with respect to time will give you a1, and differentiation of v2 with respect to time will give you a2, that is 0. So from here you will get a1 equals to minus of a2, right? So you see that here we have very clear relations going on, right? So right now you see that you can relate the accelerations and velocities and displacements of the individual particles with the help of this little constraint, right? So this simplest machine is following this little constraint. Now we can also form a constraint equation for a much complicated system and relate the acceleration of the individual particles. Here you see what is happening. We have two blocks. You see, this is block number 1, a bigger block, and block number 2. They are connected with multiple pulleys and strings, right? If you move one block, the other has to move as well. So you see that their motions are interconnected with each other, right? So now what is going to happen? So, but they have to follow one constraint because they are connected with the strings. They cannot move independently and indefinitely. So you see that if I call the length of this side is x1, and then I can assign the length of remaining values. So let's say that this is a common point passing through the center of this pulley, and let's call this value as x2. Let's call this value as x3. Right, you will see why I'm assigning these values very soon, and let's call this value as x4, right? Now, you see that one thing is pretty clear, that x1 and x2, this is forming x1 and x2. If you add them up, this will give you the length of the first string, yes or no? This will give you the length of the first string. So x1 plus x2 is a constant, that is the length of first string. So this constraint is there, right? Now this side plus this side plus this little side, that is forming the second string. So what is this little side of the left side of the second string? So we have the total thing x1, and from here to here it is x2. So the left side is x1 minus x2, x1 minus x2, and the right side of this thing is this whole thing. From here to here it is x3, and from here to here it is x2. So x3 minus x2 is this side. So x3 minus x2 is this side. That is going to give you the length of the second string. I can also rewrite this equation by rearranging x2 and x2 together, and I can say that x1 minus x1 minus 2x2 minus 2x2, x2 and x2 together, 2x2 plus x3 is equals to L2, right? This is the second, this is the constraint that we have to follow for the second string. Now, similarly for the third string, left side is this much. You see that left side is this much. So you see the total thing is x1, and from here to here it is x3. So x1 minus x3 is left side of the smallest string. So x1 minus x3 is the left side, and the right side is going to be total is x4, and from here to here it is x3. So x4 minus x3 is the right side. That is the third string. So you can also rearrange this equation and put the x3 and x3 together. So you have this thing x1, x1 and then 2x3, and then x4 is remaining. That is equals to L3. So now you have three constraints in terms of L1, L2 and L3, right? So you have the total length of the string. The value of x1, x2, x3, x4 will change as the blocks will move, but what will not change is the total length of the strings. That will not change for sure, right? So now you see that we want to relate the acceleration of first particle and second particle. You see that which of these parameters will decide the acceleration of first and second? We can say this one, x1, rate of change of x1 will decide the velocity of x1, or in turn rate of change of v1 will decide the acceleration of x1, the acceleration of the first particle. So we can say that x1 will decide the acceleration of the first one, and similarly for the second one is following this distance totally. So you see that how quickly this x4 changes will decide the velocity of the second particle, and that let's say call it v4, right? And how quickly that v4 changes, that will decide the acceleration of the second particle. So you see that acceleration of the first particle is dependent on x1, and acceleration of second particle is dependent on x4, right? Because how far the second particle is, it is x4, right? So in short, we want to look at two terms from here, this one and this one, x1 and x4, right? These are our key terms. These are our terms of interest, how far the first particle is and how far the second particle is, because differentiating that will give us their velocities and accelerations, right? So now you just differentiate it with in terms of with respect to time. So you will get velocity relations. Again differentiate it, you will get acceleration relations. So I will directly write the acceleration relation, right? So the first one differentiation will give us a1 plus a2 is 0. So you see that a1 plus a2 is equals to 0. This is the first equation. The second equation will give us a1 minus 2a2 plus a3 equals to 0. So a1 minus 2a2 plus a3 equals to 0. Okay. And for the third one, you will get a1 minus 2a3 plus a4 equals to 0. Alright. You want to relate a1 and a4 so that you can relate the acceleration of the first particle and the second particle. Acceleration of the first particle is a1, how quickly this x1 is changing, right? That will decide that acceleration of the first particle. And a2, the acceleration of the second particle is not a2. Acceleration of the second particle is how quickly that x4 is changing, right? x4 is changing. So yeah, so just you know, you can omit all the other variables from this thing. So let's try to solve the equation 1, 2 and 3 again, right? So how can you solve it? So from here you see a1 is minus a2. From the first equation you can easily say that a1 is minus a2, right? And from here you can simply replace it, right? So you can get the value of a3. You want to get the value of a3, so remove the a2 here. So in place of a2 you can put minus a1, no problem with that. So from this equation you can get a1, minus, in place of a2 you can get minus a1. So in place of a2 you get minus a1. So just when you put minus a1 here, so it will become plus 2a2, plus 2a1, right? Plus a3 equals to 0. So from here we will get a3 equals to minus times 3a1, right? Now everything becomes very easy. Now the third equation is telling you, right, a1 minus 2a3 plus a4 equals to 0, right? So from here you just put the value a3 is minus 3a1. So you just put it, a3 is minus 3a1, a3 is minus 3a1 plus a4 equals to 0, and very easily you can get it that a1 plus 6a1 plus a4 equals to 0, or a4 is minus 7 times a1. You see that? a4 is acceleration of the second particle, right? And a1 is acceleration of the first particle, and this is the relation of acceleration of first and second particle. I hope the idea is very, very clear, right? That is the idea of constraint relations, right? So following the given constraint, here the length of the strings for our constraint, following the given constraint in the equation, we can solve, we can get the relation of acceleration of individual particles when the whole system does not share a common acceleration, right? So this was the topic of constraint equations as well. So now let us move ahead and talk about the next idea, which is the part 3, which is nothing but friction, right? So let's have a discussion about the friction as well. Again, a very interesting topic. Let's have a look at each topic one by one. So here you have it. So what is friction? So you see that friction is a contact force, a type of contact force, and it only comes into the picture when the surfaces that come into the contact are rough by nature, right? So you see that here the guy is pushing this almirah, right? So it is placed on a rough surface, and almirah itself is also rough. So what will happen when he is pushing it? He is getting some sort of opposing force, opposing contact force, that is the force of friction, right? So friction acts in different situations. The first type of friction that we have is the static friction. As the name suggests, in this situation the friction force will be acting and the body will be stationary. What do you get from this idea? If I have this surface, right, my hand is rough, this block is rough, this block is resting, this rough surface is resting on my hand. Is there any static friction right now? We can say if there was a net force, if there was friction acting right now, the body would have only that friction force. Let's say friction force in that imaginary situation is 20 Newton. So I'm not applying any other force in forward or backward direction, and only friction force is acting. So friction would be the only force. So the body will start moving under the influence of that 20 Newton. That means it is not possible. The body is stationary. So in that situation, there is no force along x-axis. That means static friction is there between the rough surfaces, but under a very special condition. You see, this is a rough surface and another block is resting on it. So both the surfaces in contact are also rough. Now the friction between them will act only when you start applying an external force. Okay. So you apply a tiny bit of external force and you saw that the block is not moving. So something must be opposing, because if there was no opposing force and this is the only force that you are applying, so the net force is the external force and the body will start following the net force, right? So right now the body is not moving. That means the net force is cancelling out. So what is cancelling the net force? Here, this force, right? It is the friction force acting on the block. So I should be making that arrow near the block so that it becomes more clear. And like all other forces, it is also action reaction by nature, right? So you see that over here the friction force is acting on the block in this way. So you are applying the external force in this way and the friction force is acting this way. Both the forces are same. You increase the external force a little bit, you found that the block is still not moving, right? That means that this force, the friction force, has increased now. Okay, right? Now you increase it even further, right? Let's say initially you applied 0.1 Newton, the block didn't move. The block didn't move, that means the net force was 0 and the friction force is also 0.1 Newton. You applied it and made it 1 Newton, still the block didn't move. So the opposing force must be 1 Newton. You applied it, made it 10 Newton, still the block didn't move. That means the opposing force now is 10 Newton, right? So can I say that this static friction acts when a external force is acting on a body that has rough contacts, okay? So external force must be there and the rough contact must be there, clear. And the static friction is not constant, it is self-adjusting by nature and it adjusts its magnitude based on the value of external force. If the value of external force rises, this self-adjusting force of the static friction also changes, and in such a way that it is always equal to the external force. But can you say that it will indefinitely increase? No, that's not the case. Beyond a certain value of external force, this static friction cannot resist. That condition, or we can say that last condition that can be resisted by a pair of surfaces, is called the limiting friction. Beyond that limit, if the external force rises up, the body starts moving and the net force is there. Right, so here you have it. Let's say you applied 19.9 Newton and the block didn't move. So that means you were being opposed by 19.9 Newton. You applied 20 Newton and that is last, right? And the block didn't move. You were opposed by 20 Newton. That is the limiting friction. That is the maximum possible value of friction that can act between the surfaces. Beyond that, if you apply more than 20 Newton, the block will start moving, right? And now the static friction is not acting. Now another type of friction will start coming into the picture that acts between the rough surfaces when they are sliding over each other. It is called sliding friction or kinetic friction. We will talk about that as well. But for now, we are talking about only static friction. So you have seen static friction can be one maximum value or lesser than that. So if the maximum possible value of static friction between two surfaces is 20, that doesn't mean always 20 Newton will be acting. If the maximum possible value that can act between two surfaces is 20 Newton, but you are applying only 1 Newton, so you will only get opposition. The static friction will only be 1 Newton because it is self-adjusting. If the maximum value is 20, but you apply 10, you will only get 10 Newton, right? So idea is very, very clear, I believe. The maximum possible value of static friction is mu s into n. What is mu s? Mu s is the coefficient of static friction between two rough surfaces. We can calculate that as well. I will show you how to calculate that for a given pair of surface with the help of a little demonstration, right? So have a look at that. So F is equals to mu s into n, right? Now, so we can say that the static friction between two surfaces will only act first of all when there is external force that is pushing the rough one's body over the other and they have a rough contact, right? So static friction is going to be either equals to mu s into n, that is the limiting friction, or it will be less than mu s into n, right? Less than mu s into n, that is the limiting friction. So maximum value comes out to be 20, but you are only applying 1 Newton external force. So that doesn't mean 20 Newton will start opposing you, because in that case net force of 19 Newton will be there. Yes or no? Are you getting it? You see that maximum value of static friction right now, let's say, is 20 Newton. Limiting friction is 20 Newton. Maximum value Fs max, it is called as limiting value of static friction, which is, let's say, 20 Newton for this pair. But you only applied 10 Newton. So you will not get opposition of 20 Newton. You will only get the opposition of 10 Newton. Static friction is self-adjusting by nature, right? So right now the net force is 0 and the body will not move. Till 20 Newton, this self-adjusting nature will continue. Beyond that 20 Newton, if you apply a force of 100 Newton, the body will definitely move because of the net force is there. So the static friction is either less than mu s into n or equals to, right? So this is the condition, right? Let's move on and talk about the next idea. N is normal reaction, right? You know, kinetic friction is there as you have seen right now. When two bodies that have rough contact, one body is rough placed over the other body, they have a rough contact, and now they are moving under the influence of external force, right? So definitely they will move. They are moving over one another. Right now, since they are rough and they are moving over one another, in that case, the friction acting between two rough bodies is called as kinetic friction, right? The bodies are rough, but they are sliding over each other. The kinetic friction is acting between them, right? So kinetic friction is, the value of kinetic friction is mu k into n. It's a constant, right? As long as the bodies are sliding over each other, the kinetic friction is same between them, right? Doesn't matter how fast or slow they are moving, right? Once the body starts sliding, the value of kinetic friction they are going to get is constant. So kinetic friction is not self-adjusting by nature, it's constant by nature, right? So here this graph is telling you this thing. This is friction, this is the external applied force. So you see that, imagine this situation, here you have a body, you are applying a force F on it. So initially the force was applied, it was quite less, let's say 1 Newton. So the friction force was also 1 Newton. You applied 2 Newton, friction force was also 2 Newton. You see that external force is increased. You applied 2 Newton, friction force was also 2 Newton. You applied 3 Newton, friction force was also 3 Newton, and so on. You applied a certain value of force and the friction force reached its peak limit, right? Now the body will not remain stationary if you increase the force further. So that force, that maximum value of friction force that you can get for this particular pair of surface is the limiting value of static friction or limiting friction, right? So limiting value of static friction or limiting friction, limited friction nahi, it is not limited friction, it is limiting friction, right? Limiting friction. And what will happen after that? If you apply the force, external force higher that can cross the barrier of limiting friction, the body will start sliding with a slightly lesser value and it will get constant. So right now the value of friction, the type of friction acting between the sliding surfaces, the sliding friction or kinetic friction, mu k into n, alright. So here it is. The next thing is angle of friction. So right now you have seen when two bodies come in contact, right, then due to the nature of interaction between them, we have two possible contact forces, right? This is a situation, right? A rough body is placed on a rough surface and we are trying to push it. So there is a static friction, right? Or any kind of friction is acting like that, right? And since the body has its own weight, so it is pressing against the surface as well. And you know that when two bodies press against each other and they make a contact, so of course they apply a force on each other called as contact forces, right? So right now it is also getting a contact force from the surface it is placed on, right? So you see that it is getting a normal reaction, one contact force, and the friction force, another contact force. The resultant of these two contact forces we can find out, right? F1 is under root F1 square plus F2 square plus 2F1 F2 cos theta, alright. So the resultant of these two contact forces can be figured out, okay? And you know that what will be the direction of that resultant? What will be the direction of that resultant? Tan alpha will be F upon N, Y upon X. So alpha is the angle from this side. So tan alpha is F upon N and that will give us mu. Mu is the coefficient of friction between them, so between this surface and the surface beneath it, right? So tan alpha is F upon N, that will be called as angle of friction. Angle of friction helps us to find the relation between these two contact forces, which is normal reaction and friction force, right? So yeah, angle of friction. Now the next thing is angle of repose. How will you calculate the angle of repose? Let us have a little demonstration for the angle of repose and understand that. Here you have it, right? So here you have it. Now what is happening? Look at this situation, my dear kids. This is a rough surface and on this rough surface I am placing this block that is also rough by nature, right? And now what I am doing, you see that, let us try to increase the angle of the block right now. You see, I increase the angle of the block like this, right? The block is not sliding downward. Something must be opposing. What is the opposing force over here? We can say the friction force is opposing right now. Good. I increase the angle further. It is still not sliding. Again, you see that there was a certain angle when the body just started to slide. You see that till here, till here, till here, the body was not sliding, again not sliding, again not sliding. And if I increase the angle beyond a certain limit, you see that right over here, the body started to slide. So that angle at which the body starts to slide is giving us angle of repose for this particular pair, right? For this particular pair. Now, once we know the angle of repose for a given pair of bodies, we can calculate the coefficient of friction for that particular pair in the lab, right? Here we have calculated, you see that for that angle, let's say it starts to slide, let's say the angle is theta, theta naught. Theta naught at which the body starts to slide is called as angle of repose, right? So what is happening? What are the forces involved in the situation? So if this is theta naught, so of course this is also theta naught, so it is mg cos theta, it is mg sin theta. So you see that mg sin theta naught is acting this way, friction force was acting other way. Of course, the body will start sliding when the mg sin theta naught reaches the limit value of limiting friction, right? As long as the static friction was higher than this force, you see that this component of the weight is trying to slide it down. As long as the friction force was enough to keep it, the body was not sliding down, right? But as soon as the value of mg sine theta naught increases, because you know sine theta increases with the as theta increases, right? If theta approaches 90, so sine theta approaches towards the maximum value. So what will happen? If mg sine theta naught is increasing, it will definitely cross the barrier of limiting friction. So this is the condition when they are equal, that is the limiting condition when the body will start sliding, and the angle will be called as angle of repose, right? So here FL equals to mg sine theta naught. So this theta naught is something we are interested in, and normal reaction is balanced by the mg cos theta, right? So if you divide it, FL upon n, FL upon n, FL upon n is tan theta naught. Let's say FL upon n is tan theta naught right now. So because if you just cancel it out, you see, so tan theta naught, sin theta naught upon cos theta naught is tan theta naught, right? So FL upon n is, if you remember, FL upon n was, tan alpha as well. Alpha was the angle of friction. So right now you see that this is also giving us the same vibe. FL upon n is giving us tan theta naught. So that is clearly the coefficient of static friction between the surfaces. So from here you see, FL in place of FL upon n, you can place mu s into n, right? Mu s as well, right? So yeah, so tan theta naught is equals to directly mu s, right? Tan theta naught equals to mu s. So this is the final relation over here. So you see that with this little experiment, once you get that specific angle at which the body just starts to slide, once you get that specific angle, tan theta naught, you put the value of that angle over here, you can get the value of coefficient of static friction between that pair, right? So very easy way to find the coefficient of static friction for a given pair of surfaces. Now, that angle is called angle of repose. So have a look at this situation. Now different questions will be there on friction as well, and we will also solve a question on angle of repose as well. So let's try to solve it. Here, look at this question and try to solve it. Find the minimum force required to move the block. In this situation, find the minimum force required to move the block, right? So here you have coefficient of static friction 0.5, block has mass of 1 kilogram. You need a minimum force that will move the block. So what is keeping the block from moving? What is stopping the block from moving? So we can say it is the static friction. You're applying the force this way. The friction force is acting this way. So the value of static friction is mu s into n, or I can say the limiting value of static friction is mu s into n. So the block can only move when you cross this barrier. So what is the maximum value of force? Mu s is 0.5. And in this specific situation, how much normal reaction you will get? Because the weight of the block is acting downward, it is mg. It is 1 into, let's say, g is 10. So 10 Newton. And upward force is the normal reaction. And normal reaction, there is nothing else except these two. So normal reaction is nothing but 10 Newtons. So the limiting value of static friction is 5 Newton. You must apply a force more than that so that it can start moving. So minimum value of force is 5 Newton, you can say. Minimum force required is 5 Newton to move it at a to move it without acceleration. So if that is acting, so yeah, this will happen. So a block of mass 1 kilogram is at rest on a horizontal table, right? A block of mass 1 kilogram is at rest on a horizontal table. And then what is happening? The coefficient of static friction between the block and the table is 0.5, okay. The magnitude of force acting upward at an angle of 60 degrees from the horizontal, that will just start the block from moving, okay, block moving is. So you see that, so here is the table and here you have the block. And right now what is happening, my dear kids? The force is acting at an angle of 60 degrees like this, right? So this is how you are applying the force. You have to find the value of force that will just start moving the block, right? And they are giving you the coefficient of static friction between the table and the block is 0.5. So coefficient of static friction between the table and the block is 0.5, okay? That's it. So let's start solving it. So here you see, you will observe a very interesting, learning from this numerical. You see, force can have two components, F cos 60 and F sin 60, okay. Clearly, the normal reaction will also act on the block in this direction. It will also apply the same force on the ground, on the table as well, but we are interested only on the block. So we will only show the forces acting on the block. Earth is applying one more force on the block, which is in the downward direction, mg, right? Earth will start applying a force, mg. All right. And as you are applying force this way, so to oppose it, a friction force will come into the picture as well. That will also act on the block. This is the friction force, right? Okay. So right now, because we want to find the condition that will start moving the block, so we are dealing with a limiting value of friction. So we will find the limiting value of friction, which is mu s into n, right? So right now, what is happening? If you just try to balance out the forces on the block, right? On the block, one force is acting towards left and nothing else. No other force is acting towards left. And only one force is acting towards right, F cos 60. Nothing is acting towards right except that, right? So if you try to balance that, the value of friction over here is being balanced by F cos 60 and nothing else, right? The value of static friction is mu s into n, which is F cos 60. Cos 60 is 1 upon 2, right? No problem with that. The value of mu s is given. What will be the normal reaction? Now, to get the value of normal reaction, you have to apply your mind now. The normal reaction is not only equals to mg here, you see, because in the upward case, not only normal reaction is acting, F sin theta 60 is also acting. So the condition that you have is this is the upward force and this is the only downward force. So to get the value of normal reaction, you have to say that Fn plus F sin 60 is mg here, right? So here the normal reaction is not equals to mg. Normal reaction is, here the normal reaction is mg minus F sin 60. F sin 60. In place of sin 60, I can also put the value root 3 by 2. So this is how much value I will get, right? So n plus F sin 60 is mg. So n is mg minus F root 3 by 2. So I believe the idea is very, very clear. So now you can get the value, put the value of n over here. Mu s is 0.5. Mu s is 0.5. So put 0.5 over here. In place of normal reaction, mg minus F root 3 by 2. Mg minus F root 3 by 2. That is equals to F by 2, right? And now from here you can see that I can take that half over here. So 2 into half will become 1 and I can get rid of this 0.5 multiple, right? 0.5 will go on this side. 2 into 0.5 is 1, right? So this will become 1. So now it will become much easier to solve, right? So mg, this thing can go on the other side. So F plus F root 3 by 2 is mg, right? Now the mass of the block is 1 kilogram. Let's take the value of g is 10, right, for simplicity. So the 1 into 10 is 10. So just solve it. F can be taken as common. 1 plus root 3 by 2 is m into g, which is 1 into 10, which is 10 only. So the value of F is going to be, right, the value of F is going to be 10 upon this thing, 2 plus root 3, and 2 can go up. So 20 upon 2 plus root 3. This is the value of external force you need. This is the value of external force you need, that many newtons, that will just start moving the block, right? So I hope the idea is very, very clear. In this numerical, this thing was just the solution. Here you can see what is the value of friction force by simply looking at the free body diagram. But the key idea here that you had to learn was the normal reaction is not always equals to the weight of the body, and that we have looked at and that we have solved it. Now look into this numerical as well. So here what we are trying to do, we have a block and we are pressing the block against the wall, because if you don't do that, the block will fall, right? Now again you are pressing the wall block against the wall, so you are getting a normal reaction from the wall, right? And since the wall and blocks are rough, the weight of the block is still trying to move in this direction. You see that you are pressing it this way, the normal reaction is balancing it out. So you see that the weight of the block was acting downward, right? And if the surfaces were smooth, so in this direction the forces were balanced, and the net force here is in this direction. So in this direction there is no net force, and only force is acting downward, the body will start sliding downward. But it will not happen in our in our common sense. Based on our common sense, the block will stay because the friction force is also acting on the block, right? So we have to find the coefficient of static friction is 0.2. Coefficient of static friction is 0.2. What is the weight of the block? We have to find the weight of the block. So not the mass of the block, we have to find the weight of the block, mg, weight, w, right? So weight will be coming out in newtons, right? So clearly the normal reaction will act on the block from the wall like this. So the normal reaction here will be balanced by the external force, right, which is 10 Newton, like this, right? And in this direction there is friction force balancing the weight. So friction force is balancing the weight. Friction force is mu into n. Weight we have to find out. So I'm not putting mg because we have to find weight and not the mass. So the value of mu is given 0.2. Normal reaction is 10. Weight is this. So weight is going to be 5 Newton. That is your answer. Let's move on and talk about the next part. So in this question, what is happening? For the given set of arrangement, M1 is there, M2 is there, and it is hanging off a pulley, and the string is under tension T. Okay. So we have to find the minimum value of mass M1 for which the system remains in equilibrium. System remains in equilibrium means nothing is moving and no net force. System remains in equilibrium means no net force is there. Not means nothing is moving, it means no net force is there. Okay. So nothing is accelerating, I should say. System is in equilibrium means nothing is accelerating. Assume pulley and string to be massless. Assume pulley and string to be massless. So how can you solve it? Here you have M1 and M2 masses. The string is under tension T. Okay. So how can you solve it? So right now you see, if we don't want this thing to accelerate, the forces on M1 must cancel out. So on the right side if it is tension, on the left side it is only friction. So they must be balancing each other. So friction force on the block M1 must be balanced by the tension force on the block, right? So what is the friction force on the block M1? Let's call it F1. It is mu into N1. Normal reaction on this thing is, let's call it N1. What is N1? The weight of the block M1g. So N1 is M1g. So mu into N, mu into N1. N1 is M1g. That is equals to the value of tension that will be acting towards, right? So yeah. So now what will be the value of tension? From this side you can get the value of tension. T equals to M2g. So M2g is balanced by the tension. So T equals to M2g. You can put the value of T over here. M1g, and you can get it M2g, right? This is the limiting condition, right? This is the limiting condition. So right now you will have the value. So g can be cancelled out. So here we can say that what will be the minimum value of mass M1 that will get us through. So M1 is M2 upon mu. That is the minimum value of mass M1 in terms of M2, right? So minimum value of mass M1 for which the system remains in equilibrium. So it is the minimum value that will keep the system in equilibrium, right? So yeah, let's move on and talk about the next idea. If M1 is less than that, the block M2 will start pulling this whole system downward and the system will start accelerating, right? So the question is saying here, a block is lying on the inclined plane. It has a weight of 50 Newton. It just begins to slide down when inclination of plane with the horizontal is 30 degree. Find the coefficient of static friction. So you see that the condition is very simple, that we have a system like this and we have a block on the system like this, right? You see that they are telling us when the angle is 30 degree, the block just begins to slide down. You see, block just begins to slide down, right? So at the angle of 30 degree, the block just begins to slide down. So 30 degree must be the angle of repose. And you know that the coefficient of static friction is tan of angle of repose. So because 30 degree is the angle at which the block starts to slide down, 30 degree is the angle of repose. So it is 1 upon root 3, tan 30 is 1 upon root 3. That is the coefficient of static friction in this situation, right? So that's it. That's pretty much everything about the topic of Newton's laws of motion. Here I have picked most of the topics that were relevant for your NEET exam, right? And if you follow through each and every numerical that I have told you, you will be able to solve the DPP as well. Now I'll tell you that go ahead and practice for yourself. A DPP is shared with you containing a lot of questions, right? They are all good selected questions, right? And whatever questions I have solved over here are, you will find that they will guide you, they will help you to solve those DPP questions as well. Some questions might challenge you, and for that, you might have to use your own mind as well. That is the purpose of practice as well, right? So that's it. On that note, I'm ending this topic, and we will start the next topic soon enough. Till then, take care. Bye bye.